Now, in order to get started with TypeScript, the first thing that we need to do is to install the Node.js runtime. Node.js is a standard development tool used for developing both backend as well as front-end applications for JavaScript as well as TypeScript. Now, in order to install Node.js, open up your browser and head on over to nodejs.org. Now, the homepage will try to give you a version of Node.js that you should download and install for your operating system, but in case you want to look at all the available options, you can head on over to the download page and then select the installer specific to your requirements. Now, once you have the installer downloaded and executed, you can verify that the installation succeeded by opening up the command prompt or terminal and running the command node ---- version. Now, the specific version of Node.js that I have displayed over here is actually not that important, as the features that we will be using throughout this course are not actually version specific. Now, the Node.js installation also installs 2 additional executables, and we will be using them throughout this course, so we can verify that they are working correctly as well by running npm ---- version and similarly npx ---- version. And that's it for Node.js installation. Now let's go ahead and use Node.js to create our first TypeScript project. We open up a new terminal session, create a new directory specific to our project, and then use the npm init command to create a new Node.js package. We additionally pass in the command line flag -y to select the default options. Node.js packages are the standard way to do front-end as well as back-end software development with JavaScript. Now, because we are using TypeScript, we will additionally install TypeScript by running the command npm i TypeScript. This will install the TypeScript compiler TSC into this particular package. We can run the version of TSC that comes bundled with TypeScript within this package by using npx tsc. And then for command line flags for TSC, we pass in ---- to initialize a new tsconfig. A tsconfig.json file is used to store TypeScript configuration options. Now, for our initial options, we use --root_dir to specify that all our source code will be located in the src folder, and then a --outdir lib to indicate that our output JavaScript code should be generated into the lib folder. Now, once this command executes, it notifies us that it's created a tsconfig.json file. Now, before we start writing TypeScript code, let's talk about IDEs. Now, my recommended IDE for starting web development is VS Code. Visual Studio Code is by Microsoft, the creators of TypeScript, and it is available for free for Windows as well as Mac and Linux. You can go to code.visualstudio.com and you can download it from the homepage, or you can head on over to the download section and get an installer that is more specific to your requirements. Now, once you have Visual Studio Code downloaded and installed, you can use it to open up the project folder that we created earlier. Now let's go ahead and create our first TypeScript source code file under source index.ts. For our basic example, we will create a message variable of type string that we will initialize to the value hello world and use the built-in JavaScript runtime method console.log to log this message to the terminal. Now, TypeScript cannot be executed by Node.js or the browsers by itself. The first step is to actually take the TypeScript source code and compile it to JavaScript that Node.js and browsers can execute. Now, in order to compile the TypeScript files into JavaScript files, we open up the terminal and execute npx tsc, and we will start the TypeScript compiler in watch mode with --watch. This means that if we make any modifications to our source code, it will recompile them on the fly. Now, on its initial compile, it's already generated the output JavaScript into the lib folder. So for our source index.ts file, TypeScript has gone ahead and generated lib index.js file. And as you can see, the index.ts and the index.js file are quite similar. The key difference between the index.ts and the index.js file is that the type annotation for the message variable, that is :string, has been removed when the TS file has been transformed to JavaScript file. Now, once we have the JavaScript file, we can open up a new terminal and use Node to execute this JavaScript file using node lib index.js. And you can see that it simply logs out the message. Now, because we left the TypeScript compiler running in watch mode, if you make any modifications to the TypeScript source code, for example, add additional text to the message variable, the compiler immediately generates the new JavaScript, and if we execute the new code using Node, you can see that we get the updated result. Now, as we've hinted before, the key difference between TypeScript and JavaScript is simply these type annotations, for example, the annotation for string. What this means is that if we try to assign something like a number to a variable that is annotated as string, we get an immediate compile time error instead of something going weird at runtime. So even if you are someone who is new to JavaScript, TypeScript is a great way to get started on your JavaScript journey, as it will help ensure that your code never has any syntactic or type errors. And with that said, congratulations on finishing the first lesson. JavaScript has a few built-in primitive types. One of them is a Boolean, which can have the literal values true or false. Another primitive type is number, which can hold any floating point 64-bit value. Then there is string, which can hold any number of characters, for example the text world. In addition to these primitives, there are two special primitives for absence of data. Undefined to indicate if a value is not yet defined, and null, which is used to indicate if a value is not present. Now, modern JavaScript also introduces two additional primitive types, the symbol type to create globally unique identifiers, and a bigint type to hold arbitrarily large whole numbers. TypeScript provides predefined lowercase type names for these JavaScript primitives. These names actually follow what these types are called within the JavaScript spec. So if we wanted, we could annotate a Boolean as a variable of type Boolean, the number as a variable of type number, the string as a variable of type string, and for undefined and null, there are predefined literal types, undefined and null, and for the symbol, there is a predefined type symbol, and for bigints, there is a predefined type bigint. Now, type names in TypeScript generally follow the Pascal case convention. The only type names that are lowercase by default are these types, as these are known as primitive types in JavaScript and are fundamental to how JavaScript works. Now, JavaScript, despite being a functional programming language at its core, does support classes, and there are a number of built-in classes for JavaScript runtimes out there. One of them is the class for regular expressions. Another built-in class that is used quite heavily within JavaScript code is the class for an array. Now, because arrays are something that you will use quite heavily, JavaScript provides special syntax to create JavaScript arrays. Now, modern JavaScript runtimes also come with additional collection classes, and one of them is the set class, which is used for a unique set of items. We can initialize a set with a JavaScript array, and internally it will remove any duplicates that are found within that array. Now we can annotate instances of these classes simply by using the class name. Now for classes like array that support generics, and don't worry, generics are something that we will look at in another lesson, you will also have to pass in the generic argument. Since we have an array of numbers over here, we will use the annotation array of type number. Similarly, we have a set of numbers over here, so the annotation for that will be a set of type number. Now, in addition to these and other built-in JavaScript classes, you can actually create a class in JavaScript yourself as well. Here we have a generic class for a queue, which is a first in, first out collection. Now we will have a separate lesson on JavaScript classes as well, so the details of this class are not that important. Now, just like the built-in JavaScript classes like array and set, we can use the user-created class in a type annotation. Here we have a variable queue, which is annotated to be a queue of type number. Now, we've already looked at JavaScript arrays in a previous lesson, and we've discussed how we can annotate it using the array class name, passing in the generic argument. Now, arrays appear quite heavily within JavaScript code, so TypeScript provides a nice shorthand syntax for declaring arrays, where you simply put in the type of the members of the array, followed by the square brackets. Now, arrays can be of any length. You can have an array of 1 item or an array of 5 items. However, all items of the array must match the type that is used in the type annotation. Here we have an array of numbers, so if we try to assign an array of strings to this variable, we will get a compile time error from TypeScript. Now sometimes you want to declare an array of a fixed length. An example of that is an array with two numbers which can be used to represent a point in space. A fixed length array is commonly called a tuple in programming jargon, and TypeScript supports declaring tuples within its type system. Here we've declared a tuple of two members, and both of these members must be of type number. We can use this to represent a point in space. In terms of usage, we can assign any array of two numbers to this variable. If we try to assign an array which has less than 2 items or more than 2 items, we will get a compile time error from TypeScript. Also, the members of the array need to match the type annotation. Here we've said that both members of the array must be of type number, so if we try to assign an array that has a string in there, we will get a compile time error from TypeScript. Here we have a JavaScript variable called center that we have initialized to a JavaScript object with the members x and y both pointing to the number 0. Now the TypeScript syntax for annotating objects is very similar to the syntax of JavaScript object initializers. Here we are saying that center is a variable that must always be assigned an object with the member x of type number and a member y of type number. Now we might have multiple variables within our code that all follow the same structure. For example, here we have another variable called unit that has the same structure as the variable center. Now instead of having to copy these inline types again and again, TypeScript allows us to define and reuse types by using a type alias. The general syntax for creating a type alias is to use the type keyword followed by the name you want to give the type, here we're calling it point, then the assignment operator followed by anything that can be used in a type annotation. Now once we have the type alias created, we can use it in any of our type annotations. So we can replace what we had inline previously by the name of the type alias. Now using a type alias has two advantages. One, it allows us to name our intent. So our intent for these objects is to represent a point in space, and that is represented by the name of the type. Second, it allows us to remove code duplication, resulting in greater code maintainability in the long run. Let's create a simple JavaScript function that is designed to add two numbers. Now just like we can annotate variables, we can also annotate the parameters of a function. TypeScript also allows us to annotate the return type of a function using the same familiar syntax. Now you can have a function in JavaScript that is not designed to return any value. Now if a function does not return any value, you can annotate its return type using the special TypeScript built-in type called void. Now JavaScript also allows you to create a function that can take an indefinite number of arguments. The way to indicate this in JavaScript is using 3 dots before the parameter, and such a parameter is called a rest parameter. Here we have a function sum that you can invoke with as many numbers as you want. Internally, all these arguments get collected into a JavaScript array for the rest parameter. TypeScript understands this and will enforce that you annotate the rest parameter as an array. For our sum function, we expect only numbers, so we have annotated it as an array of numbers. Now JavaScript also supports first-class functions. What this means is that we can store functions in a JavaScript variable. Now TypeScript understands this and provides a nice shorthand syntax for declaring variables of a function type. The syntax consists of listing out the parameters between brackets, each parameter with their own type annotation, followed by the arrow operator and the return type. Now as we mentioned before, anything that is used as a type annotation in TypeScript can be given a name using a type alias. So if we wanted, we could create function types once and use them again and again. Finally, it is worth mentioning that the shorthand syntax for TypeScript function types is actually inspired by the arrow functions that are supported by modern JavaScript. Let's create two TypeScript types, a type user with a member ID of type string and a type product with a member of ID of type string. Then we have two variables, one a user and another a product. Now the structure for the user and the product type is exactly the same, that is, they both have a member ID of type string. TypeScript's type system is structural. It does not care about the names of the types. What this means is that the user and the product have the same type compatibility. This means that you can assign a user to a product or a product to the user because they have the same structure. Now let's look at another example. Here we have two types. A type for a point in two-dimensional space with the members x and y, and a type for a point in three-dimensional space with the same members as well as an additional member z of type number. Next we create two variables, one of type point2d and one of type point3d. An additional feature of the TypeScript structural type system is that extra information is okay. What this means is that we can assign a point 3d to a point 2d because a point 3d does have the members that are required by point 2d, which is x and y. Now such an assignment can also happen indirectly. For example, here we have a function that expects to be passed in a point 2d as an argument. Now because a point 3d contains all the information that is required by a point 2d, we can actually invoke this function with a point 3d without any compile time errors. Now this is also called duck typing, that is, if it walks like a duck and quacks like a duck, then it must be a duck. And a point 3d has all the walking talking features of a point 2d. Now a point 2d on the other hand does not have all the features that are required by a point 3d. Specifically, it is missing the property z of type number. Therefore, if we try to assign a point 2d to a point 3d, TypeScript will raise a compile time error. And similarly, if there is a function that expects a point 3d and we try to pass in a point 2d, we will get a compile time error from TypeScript. Let's talk about JavaScript classes. Here we have a class animal with the property name, a constructor function that is used to create instances of this class, and a method called move that takes a distance in meters and logs out something to the console. We create a variable to store an instance of this class, and then we can call methods on this instance. Now TypeScript already understands all the information that is present in the code right now, but additionally it allows us to annotate any of the properties, the parameters of the constructor, as well as the parameters of the methods, as well as the return type. TypeScript also allows fine-grained access control of the properties and methods of the class. Now by default, all properties and methods are public, which is the standard for JavaScript. However, we can be explicit about this access by using the public keyword before any of the properties or methods. Now there might be some class members that we do not want to be accessible outside of the class body. For example, we might not want the name property to be accessible outside. In order to limit the access of a member only within the class body, we can use the TypeScript keyword called private. And now any access outside the class body results in a compile time error. Now JavaScript also supports class inheritance, so we can create a class called bird that extends animal and has an additional method called fly. Now as mentioned, private members are only accessible in the class body, so we get a compile time error when we try to use the name property in the child class. TypeScript provides another access modifier called protected, which still keeps the member inaccessible on instances, however makes it accessible within the class hierarchy, so we can access this name property from the child bird class. Here we have a simple TypeScript class with a property, a constructor, and a method. Now as mentioned before, TypeScript is configured using a tsconfig.json file. Within that file, we've set the compiler options target to ES5. What this means is that when TypeScript will compile the TS file into its corresponding JS file, it will emit a version of JavaScript that can be run on an ES5 runtime. Now classes are not something that are supported by ES5 runtimes, however they can be simulated by JavaScript functions. And indeed, that is the code that TypeScript will generate when we have the target set to ES5. Now if we set the target to ES2015, which is also known as ES6, which is something that does support JavaScript classes, you can see that when TypeScript transpiles the TS to a JS file, it generates a JavaScript class that is very similar to the original TypeScript source code. Now an even newer feature for JavaScript classes in modern specification is private fields. Now they are very similar to the TypeScript specific private access modifier, and the way they work is that we have to name the field with a hash in the beginning. Now going back to the TypeScript compiler options, ES2015 is not something that supports private fields. So TypeScript will generate JavaScript that can be run on an ES2015 runtime, however it will be a bit more verbose in order to provide features similar to private fields. Now this generated JavaScript relies on an ES 2015 feature known as weak map. Now there is a special value within target called ES_next, which is a way of saying that we want to target the most bleeding edge JavaScript runtimes out there. Now with the target set to ES_next, you can see that the generated JavaScript is identical to the input TypeScript source code, except of course for the type annotations. Now, not all features of modern JavaScript can be transpiled into something that can be run on an older JavaScript runtime. As an example, let's go ahead and set our target back to ES5. Now since private fields rely on an ES 2015 feature known as weak map that is not supported by ES5, if we try to compile this code using TypeScript, it will give us an error specifying that the target is too old. Now just as a side note, for this particular example, we don't actually need to use private fields within TypeScript, as we can simply use the private access modifier. Now just like TypeScript type annotations, the private access modifier is something that is only used for compile time type checking and does not actually need any JavaScript runtime support. Here we have a simple JavaScript class that implements a first in first out collection, which is also known as a queue. It provides two methods, push to push items into the queue and pop to pop items out of the queue in a first in first out manner. Now this is a general purpose queue and it supports items of any type. So we can push in a number and we can push in a string. However, because it supports items of any type, when we pop out items from the queue, we do not get any guarantee about what the type of that item will be at compile time. So a developer's assumption of what a popped out item might be, for example in the second call, based on the toPrecision call, it seems that the developer is expecting a number. However, since the type of the items in the queue was not constrained, we were allowed to push in a string, and this particular call will result in a runtime error. Now in a language that does not support generics, we can overcome this issue by using class specialization. So what we do is that we extend the base queue class with a class specially designed for a particular item type, where we annotate the push and the pop items with that item type, and within the method bodies we simply call the superclass methods which support all data types. Now when we expect to be working with numbers, instead of using the base queue class, we create instances of this number queue, and this highlights errors when we try to push in something that is not a number, and therefore when we pop an item, we can be guaranteed that it will be of type number. Now creating these class specializations specifically for the purpose of data type annotation can quickly become cumbersome. For example, if we needed a queue of strings at this point, we would have to duplicate this code only to change the annotations from number to string. Fortunately, TypeScript does support generics, and so we don't need to create these specialization classes. So let's get rid of this number queue class and go back to our original example. We can add a generic type parameter as an argument to the queue class. And then we can use this type to annotate our push and pop functions. Now when we create instances of the queue class, we can pass in the generic type argument. For example, if we want a queue of numbers, we pass in the type number. Because we've annotated the push method to only accept items of type t, when we are passing in the generic argument number, this ensures that the instance will only accept items of type number for the push call. So we get an error when we try to push a string, and we can easily fix it. And now our toPrecision call will work because we are only pushing numbers. So to summarize, generics allow you to add type arguments that can be used to enforce a relationship between different members of a piece of code. Here we are using a generic argument in the queue class and storing it in type t. We use this to ensure that only items of type t are accepted by the push method and subsequently returned from the pop method. In this lesson, we will look at the any and the unknown types in TypeScript. To understand the behavior of these types, we start by creating variables, one annotated as any and a second one annotated as unknown. Both any and unknown are universal supertypes in TypeScript. This means that all types of variables can be assigned to something that is any, and the same is true for unknown. And that is where the similarity ends. Let's first take a closer look at any. Any is like an escape hatch in the type system. It gives you complete freedom to do anything you want to do with the variable without having to worry about TypeScript adding its type checks into the mix. For example, you can access anything you want from it, and any member access is further inferred to be any, so you can build up any ridiculous chain that you can imagine. Similarly, you can even assign it to well-defined types like Boolean without having to ensure that the value currently held by the any variable is actually a Boolean. Essentially, the any type exists to allow you to completely bypass the TypeScript type system, and you can use it to overcome pesky type errors if you are in a rush and trust that the code works. Unknown is different and safer. You can still accept anything into an unknown, but you cannot just use it in an unsafe manner. For example, you cannot willy-nilly access any properties on it, and you cannot assign it to well-defined types like Boolean without further checks. All attempts to do so will result in a compile time error. And that is the main value proposition of the unknown type. If you want to use it as a string, you have to check that its current value is going to be a string. And if you want to use it as a Boolean, you have to check that it is going to be a Boolean. So unknown can be thought of as a more type-safe version of any. It still allows free access to all types within the type system, but does so in a safe manner. The main reason why any was added to the TypeScript type system was to allow easy migration of JavaScript code to TypeScript. For example, here we have some JavaScript code that uses zero type annotations, and you can see that it works without any compile time TypeScript errors. Now the main reason for that is that unannotated variables in TypeScript are inferred to be any. To migrate this JavaScript to annotated TypeScript, we can simply add an explicit any annotation. And that's the quickest solution. But here TypeScript is not doing any hand-holding in the form of type checking for you. So if this JavaScript function loadString returns something that is not a string, for example an undefined, the code will blow up at runtime. And that's where the unknown type comes in handy. If you have time to do reliable refactoring of your JavaScript code, you can annotate the legacy variables as unknown. And TypeScript will warn you at each instance where you try to use the value from the variable, allowing you to add sanity checks before using it. So if you want to use it as a string, you need to add an explicit JavaScript runtime check, for example using the typeof operator, and similarly if you want to use it as a number, you will need to add an explicit check. So in summary, if you want a quick fix migration, use any. But if you have the time to do more reliable refactoring or are dealing with code that you don't trust fully, use unknown. This might even help you understand the code a bit better. Here we have a log function that we want to support logging for any type of variable that might be passed into it. Now you might be tempted to annotate such an input value as any. However, doing so will result in a decrease in type safety. An inexperienced developer might end up using the input value within the function in an unsafe manner because they might only be thinking of a limited set of examples, for example, just the number type. And then the code will blow up at runtime for anyone else because the body of the function is unsafe for anything other than a number. Now the recommended way in TypeScript to accept all values within the function with type safety is to use the unknown type. Externally, your function still accepts all types just like any, but now internally you get type safety when trying to use the variable in an unsafe manner. So if you want to call some method on the parameter, you need to check that the passed in parameter is actually of a type that supports that method. Getting started for front-end development with TypeScript is extremely easy. Two of the top frameworks out there, which is Angular and Vue, are actually written in TypeScript, and the most popular framework out there, which is React, supports TypeScript out of the box. Let's look at how we can create a front-end React application using TypeScript. React comes with a package called Create React App, which takes care of all of the boilerplate code that you need to create a React application. So we open up the terminal and run npx create react app, passing in the name of the application. For our case, we'll use the name example. And because we want to use TypeScript, we pass in the additional command line flags, --template, TypeScript. This will install everything that is needed by a React application and set it up for us in the example folder. Once the installation is complete, we simply cd into the example directory and open it up within our IDE. As you can see, it has created a lot of the files for us, so we don't need to worry about creating them ourselves. It has the TypeScript configuration under tsconfig.json, and all the package dependencies are specified under package.json and already installed for us into node_modules. Additionally, the package.json also specifies scripts that we will be looking at in this lesson. All the source code is located in the source folder, and our main application component is in the app.tsx file. A tsx file is the same as a ts file, and the only difference is that a tsx file supports JSX. JSX is a way of writing HTML within JavaScript, and since this file is a TSX file, all of this HTML will additionally be type-checked by the TypeScript compiler. Now let's look at some of the scripts that come pre-configured with Create React App. We open up the terminal and run npm start to start working on our application in live development mode. This starts a development server which compiles the TypeScript source code on the fly into JavaScript and serves up our application at a particular URL and even opens up the browser for us at that URL. As you can see, our UI application corresponds to the source code within app.tsx. Now let's make some modification to our UI application. We turn the text Learn React into Learning React. The live server reloads the browser, and you can see that the text is updated in the UI application with Learning React. And that's it for the development workflow. We can make any additional modifications to our source code and the browser will live reload. Now let's look at how we can deploy our application once we are ready to publish. Our UI application is designed to run completely within the browser, and the only support it needs from a web server is something that can serve up static files. In order to build these static files, there is a command called npm run build. This takes all our TypeScript source code and any static assets found within the public folder and bundles them up into the build folder. Now the next step would be to deploy this build folder to any static file hosting server. We can even run a static file hosting server ourselves by using the serve npm package. To run serve locally, we run npx serve, passing in the name of the folder that we want to serve, which in our case is build. Once this command completes, it starts serving up the build folder and copies the URL that we can open up in our browser to visit the build application. As you can see, our final application is same as the application that we were building using npm start. Now there is a lot more learning you can do on your framework of choice, be it React or something else, but rest assured that once you know TypeScript, getting started is simply a matter of reading the framework startup guide. Here we have a variable that is initialized by a function call. Now we know that this function is returning a string, so we try to use the variable as a string and trim its value. And we get a compile time error. Now the reason for the error in this particular case is that the load function is annotated to return an unknown type. It is possible in TypeScript to end up in a situation where either the function annotation is incorrect or the type inferred by the TypeScript compiler does not match what you know the value of the variable to be. Of course, for the unknown type in this particular case, we can add a JavaScript runtime type check to ensure that the value of the variable hello is string before calling the trim function. Now you might not want to add this runtime type check simply because of performance reasons, or you want to save some time and simply develop your application without having to worry about the types. For this reason, TypeScript provides you with the concept called type assertions, which you can use to tell the compiler what the type of a variable is without having to do any of the type inference or type checks. With the asString type assertion, we are telling the TypeScript compiler that, dear compiler, trust me, I know this is a string, you don't have to second guess it. And with that in place, we can use this variable hello as a string and call its trim method. The main syntax for a type assertion is the as keyword followed by the type that you want to assert. Now TypeScript also provides an additional syntax for type assertions known as the angle bracket syntax, where you put the type in angle brackets before the variable. Now I don't recommend that you use the angle bracket syntax as it does not work in TSX files. To demonstrate that, let's copy this code into a TSX file. Now TypeScript will immediately give you an error, and the reason for this error is that it thinks that this is a JSX element instead of a type assertion. Of course, you can still do type assertions in TSX using the asType syntax. Now before we finish, beware that type assertions are your way of telling the compiler that you know better than what it understands. The ideal approach, of course, is to use proper type annotations or runtime JavaScript type checks to ensure correct type inference. Coming from other typed programming languages, you might be familiar with the concept of typecasting. Here we have a variable of an undeclared type that we later initialize to a string, and then if you want to use this variable as a number, you might be tempted to use a type assertion of TypeScript to convert it to a number. However, a type assertion is not the same as typecasting. This is because the value currently held by the variable will still be a string, and if you try to compare it to a number at runtime, you will find that it is not a number because its value is actually the string 1337. Now TypeScript doesn't support any special syntax for typecasting. However, it understands how typecasting works in JavaScript, so you can use your JavaScript tricks to do any typecasting that you need. For example, a common way to convert a string to a number is using the plus operator before the string. Now TypeScript understands the impact of using the plus operator, so now if you hover over the number variable, you can see that TypeScript has inferred that it is going to be a number. Now this type of type manipulation within JavaScript documentation is called type coercion, and with that in place, the variable number will be a number at runtime. Here we have a JavaScript function that determines if a particular string is a palindrome or not. Then we use this function with two examples. First, Madame, which is a palindrome because it reads the same forwards and backwards, and then another example that is not a palindrome. It's great that we can use this function within this file, but what's even better is if we could use this general purpose utility in other files in our codebase. The solution to this task is provided by JavaScript modules, which are also supported first class by TypeScript. As an example, let's go ahead and export this function from this file using the export JavaScript keyword. That makes this function importable by other files within our codebase. As an example, let's jump to another file in the same folder. Now the first step is to import the module into this file. The general syntax for importing modules is import followed by the kind of import, followed by the keyword from, followed by the path to the module. In our case, the module is located in the same folder in a file utils, so we can use the relative path /utils. Now TypeScript understands everything that is exported from this module and will provide you with nice autocomplete and error checking in case of any mistakes. For our use case, we simply import the function isPalindrome, and now we can cut the usages of the function from utils.ts and then paste them into index.ts, and because of that import, they will now work as if this function was locally defined within this file. As a final note, all of the syntax of JavaScript ES modules is supported by TypeScript. For example, we can bring in the module as a namespace import into a namespace called utils, and then for usages, we can access the function isPalindrome from this namespace. The standard way of accessing environment variables within Node.js is using process.env. Here we have a simple piece of code that logs out the logged in user. However, you can see that we are getting an error on the process variable. If you hover over the error, you can see that it is complaining that cannot find the name process. This is because process is not defined anywhere within our codebase, and we expect it to be provided by the Node.js runtime. TypeScript provides the ability to declare any variables that are not present within the TypeScript codebase. For example, for the process variable, we can simply declare it as a variable of type any. The syntax for a type declaration is the same as the syntax for declaring any other variable within your codebase, with two key differences. First, we use the declare keyword before declaring the variable, and then we cannot provide any implementation details as they are not really a declaration, but rather a definition. For example, if we try to provide a value for the process variable, TypeScript will complain that you cannot provide any implementation within a declaration. TypeScript supports creating these declarations within a separate file as well. These files are called declaration files. A declaration file is simply a set of declarations and has the file extension .d.ts. So we can take the type definition for the process variable and create a new file called env.d.ts, and you are free to name your declaration files whatever you want as long as they end in .d.ts. And then we paste this declaration for the process variable. Now, in addition to this process variable, there are a lot of other Node.js runtime features as well, and we could keep going down this path of creating these declarations ourselves, but fortunately there is a better way. So let's go ahead and delete this declaration file and compile the code using the TypeScript compiler. Now you can see on the compiler output that not only does it tell you that it cannot find this process variable, but also provides a suggestion that you might want to install the type definitions using npm i types node. Now types is the name of an npm organization owned by Microsoft, and packages under this organization are automatically deployed from a very popular community-driven open source project called Definitely Typed. One of the many type definitions is the one for Node, and we can install it by running npm i add types/node. Once the installation is complete, you can see that the error for the process variable goes away, and the same lack of errors can be observed if we compile our code using the TypeScript compiler. Now if you go to the definition of the env variable within our code, you can see that it comes from a file called process.d.ts, which is a part of the package that we installed, which is add types/node. Now the Node.js runtime also provides a number of built-in modules as well, and one of them is for file system known as fs. Now in order to use fs or any of the other modules, we simply import it within our code and use it as you normally would within JavaScript. Now one great thing about these type definitions worth mentioning is that in addition to providing compile time type safety, they also provide great docs for all of the APIs that you are using, for example for this write file sync function. That's it for the Node.js built-ins. Let's talk about third-party packages that you might find on npm. Now many of those packages are written in TypeScript, so you don't need to do anything special other than simply installing them in order to use them in your code base. There are, however, some packages that require an external type definition, and one such example is Express. If we simply install Express and try to use it in a simple JavaScript application where we create an Express application, set up a route, and start listening, you can see that we get a few errors. The key one here is that the Express module is not found because it is not described anywhere in TypeScript. Similar to what we did for Node, we can actually simply install the type definitions for Express that are maintained by the community using npm i types/express. Now once the installation is complete, you can see that the errors within our IDE go away, and if we run the compiler on our codebase, we don't get any errors on the terminal. We create a new directory for our package and then cd into that directory. Next, we initialize a new package.json by using the familiar command npm init -y. Now because this package will be written in TypeScript, we install the TypeScript compiler with npm i TypeScript and save it as a dev dependency with -D. Now we use this installed compiler to initialize a new tsconfig.json by running npx dsc --init. We also specify a few compiler options for the generated tsconfig. We specify that the root directory will be the source folder, which will contain all our TypeScript source code, and the output directory as lib, which will contain all the generated assets. We enable source maps so we can debug the source code TypeScript from the generated JavaScript. We enable declarations so that the compiler generates type definitions which can be used by our TypeScript consumers. And we enable declaration map, which allows our TypeScript consumers to navigate from the type definitions to the TypeScript source code. We will see these output source maps, declarations, and declaration maps when we run the compiler against our source code later in the lesson. Now let's open up this folder within our IDE. For this package, we will create our main entry point under source index.ts. In terms of code, we can put whatever we want in this package. For example, we can use a familiar isPalindrome function and export it from this main module. Now we will make some minor tweaks to the package.json file. Our main application entry point will be generated in the lib folder, so we change main to be lib, and because we will be generating TypeScript type definitions as well in the lib folder, we add a section for types and point it to lib as well. In terms of building our package, we can run npx tsc on the terminal if you want, but we can also add a special script specifically for compiling using TypeScript. We call this script build, and within this script, we will simply run tsc for the TypeScript compiler. Now let's open up the terminal and execute this build with npm run build. Once this build completes, it generates the output assets within the lib folder, and you can see that we have the output JavaScript as well as the source map, as well as the declaration, as well as the declaration map. Once we are happy with our TypeScript source code and we have the assets built, we can publish these to npm by running npm publish. This makes this package available for use for anyone else through npm. That's it for creating an npm package. Now let's look at how we can consume it. Now in terms of using this package, all that we need to do is to install it using npm I package name, which in our case is Pelend. Once the installation is complete, you can import this package just like any other module within your codebase. And then we can use this package with complete IntelliSense and compile time type safety and all the other benefits that TypeScript provides. We don't have to do anything special in order to use a package written like this. For example, at this point, we can simply run npx tsc to compile our application and then run it through Node, and you can see that the output matches our expectations. Here we have a simple JavaScript function that logs out the text hello world and then we invoke it. Now if you run this code, you can see it works as expected, logging out the text hello world. Now your mission, should you choose to accept it, is to log out the text 1s after 1 second, then 2s after 2 seconds, and 3s after 3 seconds. You might be tempted to do this using setTimeout. For example, here we have a timeout of 1000 milliseconds, also known as 1 second, and then we log out the text 1s. Now if you continue down this path, you end up with this chain of set timeouts for 1 second, and then the 2 seconds, and then the 3 second. And you might think that you can unwrap this by moving the set timeout externally and setting up set timeouts for 2 seconds and 3 seconds up front. But if you want to start the timeout only after the console log is complete, you will have to do this chain where you do the console log statement and then set up a new set timeout. Now in terms of functionality, you have achieved your objective that it does log out 1s after 1 second, 2s after 2 seconds, and then 3s after 3 seconds. However, in terms of code with JavaScript, we can do a bit better. The key to better asynchronous programming in JavaScript is async await. We start off by creating our main function, and the only difference between this function and the function we created before is the JavaScript async keyword before the function body. Async await works on top of JavaScript promises. Now for our requirement of logging stuff after a particular time, we want a promise that resolves after a particular amount of time. We create a utility function called delay specifically for creating such promises. The delay function takes a duration in milliseconds and then returns a new promise created using the promise constructor, and then uses the resolver for the promise to resolve the promise after the given milliseconds internally using setTimeout. Now once we have this delay function, we can use it to create a promise that resolves after a particular amount of time. For example, one that resolves after 1000 milliseconds, also known as 1 second, and then await for it to get resolved, and then log out some text, for example, 1s. And once this log is complete, we can again create a promise for 1 second and then await it, log out 2s, then create a third promise for 1 second and await it, and log out 3s. Now in terms of functionality, this code behaves exactly the same as the code we wrote with setTimeout, logging out the seconds after appropriate durations. I guess there is no doubt in anyone's mind, comparing the two codes side by side, that the async await version is so much cleaner than the nested setTimeouts. Now as far as TypeScript is concerned, it supports the JavaScript async await out of the box, and you can simply use it in your TypeScript source code as we have been doing throughout this lesson. You can even set your target to ES5, and TypeScript will transpile this into something that can be run on an older browser. Here we have a basic TypeScript source code with a single type annotation. Now TypeScript is not something that can be run natively on Node, so if you try to run it through it, you will actually get a syntax error as shown over here. Of course, the simplest way to run any piece of TypeScript code is to first compile it to JavaScript, and we can do that by running npx tsc. And now once we have the output JavaScript in the lib folder, we can simply execute it through Node. Now if you want to skip this compile TypeScript to JavaScript and then execute it process, there is an npm package called tsnode that can compile your TypeScript to JavaScript on the fly and then execute it through Node in a single step. So in order to run this TypeScript source code, we simply run npx tsnode source index.ts. This will bring in the tsnode package from the internet and then execute it locally and you can see that the output matches what we expected. Now with any npm package, if you want to skip this download from the internet flow, you can install that package into your folder. So for tsnode, we simply run npm I tsnode. And once the installation is complete, if we run the same command again, you can see that it executes much faster. Now if you find yourself running some npm command again and again, you can even move it into the package.json script section to give it a nicer name. So within our script section, we create an entry for start, which will execute tsnode for source index.ts. And now we can simply open up the terminal and run npm start, which will in turn run tsnode, and you can see that the output matches what we expected. Here we have a simple JavaScript class called person that takes an initial value for the age property and then provides two methods, one growOld, which increments the age property, and then a method called age, which returns the current age of the person. Then we create an instance of the person with an initial age of 0, call the growOld method to increment the age to 1, and then log out the age. And of course, if we run this code, we expect it to log out the age of 1. There are two ways to think about the this keyword in JavaScript. One way is the calling context, the other way is lexically scoped. Other than arrow and bound functions, this is driven by the calling context. Since the growOld method is not an arrow function, this will be driven by the calling context. So when we are invoking growOld on the person object, this will be person. Now as we've discussed before, functions in JavaScript are first class, and what this means is that they can be stored in a variable. So we can store the growOld method into a variable and then invoke it directly. Now in this case, since the method is not being invoked on any object, the calling context and therefore the keyword this will be undefined within the function body. And if we run this code, you can see that error shows up on the console. Now you might be tempted to think that you would never store a method in a variable and never end up with this code in real world. However, this method to variable assignment can occur quite easily. For example, if you give this method to set timeout to invoke later, this will be lost. As far as the invocation within setTimeout is concerned, it will be the same as just calling the growOld method by itself. Fortunately, JavaScript also offers a lexically scoped this, and the way to use that is with an arrow function. So instead of creating a simple method, we create growOld as a property pointing to an arrow function. Arrow functions in JavaScript capture this from the surrounding context. Since all property initializers execute at the end of the constructor, this will be bound to whatever instance is present within the constructor. And now, since it is no longer driven by the calling context, we don't need to worry about it being invoked incorrectly, and both our usages, both as a variable and within the setTimeout, will work as expected. So if we log out the age after 2 seconds, you can see that the answer is correct with the value of 2. Here we have a type declaring a point in 2-dimensional space with the members x and y of type number. We create a const variable declaration for this point with the members x and y both pointing to the value 0. Using a const declaration ensures that we cannot assign a different value to this variable. However, in JavaScript, a const declaration does not prevent us from assigning different values to the members of the variable. Fortunately, TypeScript gives you the opportunity to add a read-only modifier to different members of a type. So if we make x as read-only, we can no longer assign to this property after the declaration. And of course, we can do the same for the y member to make that as read-only. And of course, marking a property as read-only gives you access to read the property, you just cannot reassign it. The read-only modifier in TypeScript is a compile time only feature used for error checking and does not require any runtime JavaScript support. That's it for types. Now let's look at JavaScript classes. Here we have a simple JavaScript class called animal with a member name that can be initialized using the constructor. We create an instance of this class passing in the name sheep. Now at this point we can read the name member as well as modify it. For example, put a wolf in sheep's clothing. Now if we want to disallow the assignment of the name property after the constructor, we can use the same read-only modifier before the property name, and now if we try to write to the name property after the constructor, we get a compile time error from TypeScript. Now, just like other class access modifiers, public, private, and protected, the read-only modifier in TypeScript is a compile time only feature used for compile time error checking and does not require runtime JavaScript support. Now, one final thing worth mentioning is that we can combine read-only with other class member access modifiers, for example, public. One amazing feature within the TypeScript type system is type unions. Let's consider a simple example to demonstrate their motivation. Here we have a simple function that can operate on a string or an array of strings, and within the function body, if it is simply a string, it will trim it and return the result, and if it is an array, it will trim each of the strings in the array and then join them with the space and return the result. Such functions, which operate on a single item or an array of items, is quite common within the JavaScript ecosystem. Currently, in order to accept a string as well as an array of strings, we have this function annotated as input type any. However, this results in type unsafety. For example, someone can pass in a number and now our code will blow up at runtime without any compile time errors. Fortunately, TypeScript allows you to create types as a union of predefined types. For example, in our case, we want to accept only a string or an array of strings. Once we've added this annotation, invalid usages are highlighted as a compile time error by TypeScript. Now, union types are simply a set of types separated by the pipe operator as shown over here. You are free to use any type names separated by the pipe operator to create a union type. Let's demonstrate that by another usage. A common requirement in UI programming is to pad a string with some characters before it. Here we have a function that achieves this objective. If the input argument is a number, it pads with the number of spaces. Alternatively, you can pass in your own padding string, and that is used prepended before the input value. And if the input is not a number or a string, this function throws a runtime error. A naive approach would be to accept all inputs using the unknown type as we have done over here. And indeed, it does achieve the objective of accepting a number or a padding string. However, just like any, unknown accepts all types, and if someone were to call this function with something that is not a number or a string, for example a boolean, this function will throw a runtime exception. Fortunately, once more, we can catch this error by using a proper union type annotation for the padding parameter. In this case, we want to accept a number or a string, and anything else will be caught as a compile time error from TypeScript as shown over here. Now, just like any other type annotation within TypeScript, you can extract a union type into its own type alias, giving it a well-defined name for better code readability. Now, if your unions are becoming a bit long, TypeScript allows you to split your union into multiple lines. Also, in order to increase the readability a bit more, TypeScript allows you to optionally add a pipe before the first member in the union. This has no impact on the semantics of the type and is purely there for code readability purposes. Here we have a variable called direction of type string. Now the type string can accept any JavaScript string, for example a dictionary spelling of the word north. However, because it accepts all strings, you can even provide it with a string that is a bit poorly spelled. Now if you want to ensure that north is always spelled with the correct spelling in your codebase, there are a few JavaScript runtime solutions to that problem. For example, you can create a variable pointing to this string north and only use that variable instead of typing this string inconsistently in your codebase. Now, in addition to all the JavaScript runtime solutions, TypeScript also provides a compile time solution to this problem in the form of literal types. TypeScript allows you to use any string literal in a type position. For example, the literal string north. And now the only value that can ever be assigned to this variable is the literal string north. Any other type or string will result in a compile time error as shown over here. Now, of course, a variable that only accepts just one string literal is not particularly useful. And you would most commonly use a literal type in a union. For example, we can create a union of all of the cardinal directions that can be used for this direction variable. And now anything that is in this union will be fine and anything else will result in a compile time error. Now one great thing about literal string types in TypeScript is that they also show up in autocomplete, which can result in a great developer experience. Now just like any other union type in TypeScript, we can extract this union of string literals into a named type alias, for example called cardinal direction, and once you have this type alias, you can start using it in a library of utility functions specific to your domain. Now, in addition to literal strings, TypeScript also supports literal types for the boolean true and false, as well as any number value. To demonstrate that, let's look at another example. Now we can represent the value of a traditional dice as the number values 1, 2, 3, 4, 5, 6. And then we can create a utility function that uses math.random to roll a dice. We use the return value from math.random and scale it from 0 to 5.99999, you get the idea, and then use math.floor to limit this value to be 0 to 5, and then scale it by adding 1 to be 1 to 6, which matches our dice value type, and we inform TypeScript of this fact by using a type assertion. Now once we have this type and this utility function in place, we can start using it in our codebase, and at any point if we try to use it improperly, for example try to compare the result of a roll dice to the number literal 7, which is not a member of the dice value, we get a compile time error from TypeScript, keeping us from shipping bugs to production. This is the pad_left function that we previously saw in our lesson on union types. Now the padding parameter for this function can be a string or a number, allowing us to pad with a number of spaces or any given string. Now within the function body, we are using the JavaScript type of operator to determine if the padding is a number or a string. Outside of these conditional blocks, the padding parameter can be a number or a string. Now within these conditional blocks, TypeScript understands that if this condition is true, then within the condition body, the padding parameter must be a number. And if you hover over the padding parameter, you can see that it is inferred to be a number within this block. The same is true for the other block. If the type of padding is a string, then within the conditional block, the padding parameter will be narrowed down to the string type. Now the JavaScript type of operator is one of the ways in which you can narrow down a union type into one of its primitive members. Now this is perfectly fine if the union type that you are looking at consists of primitive members like number or string. For anything else that is not a JavaScript primitive type, the type of operator actually returns the string object and therefore cannot be used to discriminate between the members. Now let's look at how we can narrow between instances of different JavaScript classes with an example. Here we have a simple JavaScript class called cat with a single method called meow. We also have another JavaScript class called dog with a single method called bark. We can capture instances of a cat or a dog in a single type union called animal. Now we want to create this utility method called speak, which can accept any animal, and if it is a cat, it should meow, and if it is a dog, it should bark. Now as mentioned before, we cannot use the type of operator because it will be the string object for instances of either a cat or a dog. Now the proper way to determine if a given object is an instance of a class is using the JavaScript instance of operator. So we check if the passed in animal is an instance of a cat, and if so, we invoke the method meow. Otherwise, if it is an instance of a dog, we invoke the method bark. Now just like the type of operator, TypeScript understands the instance of operator and understands that if this condition is true, then within the condition body, animal will be a cat, and similarly, if the second condition is true, then the animal will be a dog. Now that's it for classes. But what about objects that are not created by calling a constructor of a particular class? Let's discuss those with another example. Here we have a type representing a square with a single member called size to represent the square's width as well as its height. Then we have this type called rectangle with separate members to represent the rectangle's width and height. Now we can capture instances of a square or a rectangle in a single type union called shape. This allows us to create a utility function called area that can operate on any given shape. So if we pass in a square with a single size value of 2, it should return the area 4, and if we pass in a rectangle with a width of 2 and a height of 3, it should return the area of the rectangle, which would be 6. Now as we mentioned before, the type of operator for both of these objects would be the string object and would not help us differentiate between a square and a rectangle. Additionally, since these instances are not created by classes, we cannot use the JavaScript instance of operator to differentiate between the two objects. Fortunately, we can use the JavaScript in operator to determine if a particular property exists on the passed-in object, and TypeScript will automatically infer that if this property is present on the object, then it must be of that particular type. So if the size property is found on the shape and this condition turns out to be true, TypeScript infers that shape must be a square. Similarly, if the width property is found on the passed-in shape, TypeScript infers that shape must be a rectangle and will allow us to use the width and the height property with complete compile time type safety. A common use of literal types in TypeScript is to have a union of types which have a single shared field. This single shared field can be used to discriminate between the members of a union. Let's discuss this with an example. Here we have two types, a square and a rectangle, and then a union of the two types that allows us to work with either a square or a rectangle with simple utility functions. Now in our area utility function, we are currently using property checks to determine if a particular shape is a square or a rectangle. If it has a member size, then it is a square. If it has a member width, then it is a rectangle. Now using these property existence checks, for example, checking if a shape has a member width does not intuitively tell us that we are checking if the shape is a rectangle. This is where a discriminated union comes in. We can add a property with the same name to all of the types in the union, but with different literal values. For example, we can add the property kind both to a square with the literal value square, and then to a rectangle with the literal value rectangle. And now because all of the members of the shape have this property, we can access it off of any given shape. Additionally, when we try to access the property, TypeScript figures out that the only literal values that kind can be is either a square or a rectangle, and will even provide nice autocomplete. And now if the kind is indeed a square, then TypeScript knows that a shape with a member size has been passed in. Similarly, if the shape.kind is a rectangle, then shape must be a rectangle with the members width and height. Discriminated unions are also easier to maintain when we need to add additional members. For example, if we decide to support the circle shape as well, we simply add the type circle with the member kind pointing to the literal circle. Then we add it to our shape union, and if we ever want to operate on a circle, we simply check that the kind member is pointing to the literal circle. Now you are free to call the discriminating member whatever you want. And in addition to string literals as we have done over here, you can also use other literal types like a boolean or a numeric literal. Let's demonstrate that with another example. Here we have a type representing a validation success, and then another type representing a validation failure, and then a type validation result, which can either be a validation success or a validation failure. Now both the success and the failure types have the same named member called isValid. The only difference is that in a validation success, isValid is pointed to the literal true, and in a validation failure, the isValid member is annotated to be the literal value false. Now using a discriminated union for validation results, as well as for network requests that might return a success or a failure, is actually a great idea. For example, in this particular case, we will not be able to read the validated value unless we ensure that isValid is true. Now let's consider a utility function logResult, which wants to log out any form of validation results. Within the function, we can simply check if result.isValid is true, and if so, we know that it is a validated value and we can log that out. Otherwise, if isValid is false, then it must be a failure and we can log out the error reason. Let's start off with the simple TypeScript class that represents a person object. Now this class has two properties, name and age. Then we have a constructor with parameters name and age, and we use these parameters to initialize the class properties. Now to demonstrate these properties, we create a person called Adam to represent the first human to ever exist, and then log out Adam's name and age. Notice that there is duplication between the declaration of the properties and the constructor parameters. TypeScript allows us to get rid of this duplication by using parameter properties. So we get rid of the property declaration and we get rid of the property initialization, and then within our parameters we can actually declare them as properties by using the modifiers public, private, protected, or read-only. This takes these class parameters and declares properties for them, and then also initializes them with the values that are passed in when creating class instances. When you use the TypeScript compiler to initialize a new TypeScript configuration using tsc --init, the generated tsconfig.json has this option called strict, which is by default true. The strict option is actually a collection of options, and if you set strict to true, all of these options are implicitly set to true. If you set it to false, all of these options become false. Now you can still override the individual options. For example, you can set strict to true and set no implicit any to false, and that will mean that all of the other options are still true, but no implicit any is false. Now let's look at the impact of setting strict to true or false with some examples. On the left we have a TypeScript file from a project with strict set to false. And on the right we have a TypeScript file from a project with strict set to true. Here we have a function that is designed to add two numbers. Now for numbers, this function is perfectly fine, and indeed when you invoke it with something like 1 and 2, you get the expected result of 3. However, notice that we haven't provided any type annotations for the parameters first and second. What this means is that TypeScript will infer them to be of type any, allowing you to invoke the function with all types, for example with 2 strings. And you might think that it is perfectly fine to do so in this case. However, the result might be surprising. You probably expected hello world, and instead you got world hello. This is because the developer of the add function expected you to call it with numbers, and the order of parameters doesn't matter in that case. So let's go ahead and copy all of this code from strict false to a project with strict true. We immediately get 2 errors from TypeScript. With strict true, if you fail to provide type annotations for something that TypeScript cannot infer, it raises a compile time error. As an example, the error for the first parameter is that parameter first implicitly has an any type. Now the fix for this particular error is to add a type annotation, and in our case, the proper type annotation is the annotation for number. And with these annotations in place, any invalid usages, for example, an invocation with strings, will result in a compile time error, and we can go ahead and delete those. Now, of course, with strict mode, you are still allowed to explicitly add an any annotation. For example, here we have a log function that can in reality work with any type, so we can get rid of the error on the value parameter by adding an explicit type annotation of any. Now, error on an inferred any is just one of the features that are provided by the strict compiler option. Let's look at an example of a different feature. Here we have a class for a point in 2-dimensional space with members x and y of type number, and a method move that allows you to shift the values of x and y. We can create an instance of this class and then provide values for the x and y properties, and then use the move method to move these x and y by some amount and log out the result. Now at this point, all of this code is perfectly fine. However, it is not great API design. We implicitly expect that the creator of the point has provided values for the x and y members. It is perfectly possible that we might end up with the point created where x and y have not been provided. In this case, the move function will have weird results, that is, it will set x and y to not a number. Now let's go ahead and copy this code over to our project with strict true. We immediately get 2 compile time errors. The errors are that the properties are not initialized and are not definitely assigned in the constructor. What this means is that you might end up with a point where the x and y members are not actually numbers. Now one of the ways in which we can fix this error is by ensuring that we actually initialize x and y in the constructor by taking the initial values as parameters. And now if anybody wants to create a point, they will have to provide initial values, ensuring that the x and y members are always numbers for all instances of our points. Now these definite assignment checks are just another feature that is a part of the strict suite. Let's look at another example of a different feature. Here we have a type representing a user in a database with the properties name and age, and then we have an in-memory database of users with 2 members. Now if you want to get the age of a particular user, given the username, we can create a utility function which accepts the name as a parameter, goes through the list of users to find the user where the user.name matches the input name, and then finally returns the found user's age. Now this code looks perfectly fine, and indeed it does function if the user is found. Now let's go ahead and copy this code over into our project with strict true. And as soon as we do that, you can see that TypeScript has found a potential error. The error in this case is that we are trying to access the age property of a user that may or may not be found. Now this will result in an ugly runtime error like cannot read age of undefined. Now because TypeScript has caught this error at compile time, we can raise a nicer error like user not found, which is the actual source of the issue. And now thanks to TypeScript's code flow analysis, it knows that user will no longer be undefined and allows you to access the age property. Now once more, this is just one of the features that is provided by strict. Now let's jump back and discuss whether you should set strict to true or false. Enabling this option is a programming preference. If you prefer dynamic typing overall, but want as much of the free benefits you can get from TypeScript, set strict to false. But if, like me and many other TypeScript developers, you want as much type safety as possible, you should leave strict as true, which is the default option. One final consideration worth mentioning is that if you are working in an education setting, you might want strict as off to provide a more gradual introduction to TypeScript. JavaScript runtimes have two types to indicate the absence of a value. If something hasn't been initialized, the runtime normally returns undefined, and if something is currently unavailable, the runtime returns null. TypeScript provides literal type annotations for both of these values. Now you will have to deal with both of these values even if you don't use them explicitly in your code. Let's look at a few examples. Here we have a class point with members x and y of type number. We create an instance of this point and then initialize the two members. Now if by any chance we forget to initialize any of these members and try to access that particular member, the JavaScript runtime will return us the special value undefined. Now just like undefined, null is a part of many JavaScript runtime features. For example, here we have a function that logs out the vowels of a particular input value string. Internally, it uses the JavaScript built-in string match method to find any of the vowels A, E, I, O, U. This built-in match method returns an array of matches if any are found. For example, E and O match in the hello string. However, if we pass in a string that does not have any vowels, for example the string sky, this built-in method returns null. So as you can see, even without explicitly using the literals undefined or null, they might be handed over to you by the JavaScript runtime and you will have to deal with both of them. Fortunately, there is a neat way to handle both of them in your JavaScript code, and the trick is using the double equals operator. Now it should come as no surprise that with the double equals operator, null is equal to null and undefined is equal to undefined. However, what might be surprising is that undefined is also double equal to null. This means we can use the double equals to null to check if a value is null or it is undefined. Furthermore, double equals to null is not true for any other falsy values such as false or 0 or an empty string. This means that we can use the double equals to null to explicitly check just for null and undefined without having to worry about any other values leaking through. As an example, consider a function that might return you a boolean or null or undefined. That is, the result returned can be one of these three types. Now you can safely isolate null and undefined with the double equals to null check. And in fact, TypeScript understands this as well and will narrow the type for you to be just null and undefined. Alternatively, if you want to remove null and undefined from a particular set of types, the proper way to do that in JavaScript is to use not equals to null. Once more, TypeScript understands this as well and will correctly isolate that the result must be a boolean at this point, as both null and undefined have been ruled out. To give you a bit more practice with handling null and undefined in TypeScript, let's look at another example. Here we have a function called decorate that has a parameter value which has been annotated to accept a string or null or undefined. Now within the function, if we try to access the value as a string, for example, try to call the string trim method, we get a compile time error from TypeScript, and if you look at the error message, you can see that TypeScript is complaining that value might be null or undefined. Now using what we've learned just right now, we can isolate null and undefined from value by using a double equals null check. And in that particular case, we simply return the value back to the caller, and if that condition is false, TypeScript now understands that value must be a string and will allow you to safely call the trim method. And now we have a nice decorate function that can work with strings as well as with nulls and undefined with complete compile time type safety. Now one final thing worth mentioning is that null and undefined are only enforced as distinct types when the TypeScript configuration has strict set to true, or more specifically the sub-option strict null checks set to true. This is true in the default configuration created by TypeScript anyways, and I highly recommend that you leave it as that for maximum type safety. Here we have a type representing a point in two-dimensional space with members x and y of type number. Now within our library, we also want to express points in three-dimensional space, and we have the members x, y, and z of type number. Notice the duplication between the members x and y of point 2D and point 3D within the same codebase. Now you might be familiar with the concept of class inheritance. Intersection types behave in a similar way and allow you to combine the features of any two given types. So we can remove the duplication of the x and y members in the point 3D type and simply use a type intersection with the point 2D by using the ampersand operator. Here we are saying that point 3D has all the members of point 2D and the member z of type number. Now of course we can chain multiple types with multiple ampersand signs, and additionally we can use intersection types inline. Let's look at another example. Here we have three types: a type person with a member name of type string, a type email with a member email of type string, and a type phone with a member phone of type string. We have this utility function that uses the name, the email, and the phone to contact an individual. Now we can enforce that the contact function is called with all the correct details by using an intersection type combining the members of person, email, and phone. And now we get to invoke the contact function with complete compile time type safety, and if there are any type errors, for example a missing member, we get a nice compiler error from TypeScript. Now one final thing worth mentioning is just like type unions, we can extract an intersection type into a type alias, and we previously saw this usage in point 3D as well. Similarly, we can add a leading ampersand before a type intersection, and it has no impact on the semantics of the type and is there purely for readability purposes. Here we have a type representing a person with the members name and email both of type string. Now these members of the type are considered required members. In addition to required members, we can add an optional member with a question mark modifier. Here we've added an additional optional phone member to the person type. Now we can create an instance of the person type with all three members, or we can even create a person object with just the two required members, leaving out the optional phone member. Now in JavaScript, if you try to access a property that hasn't been provided, the JavaScript runtime will return the special value undefined. TypeScript understands that and will automatically mark all optional members to also include the undefined type. Now with optional members, we can leave them out as we have done for the Alfred object over here, or we can provide a member with the correct type, for example provide a string for the phone as we previously did for the Bruce object as well, or we can even provide an explicit undefined value. It is still type checked, so anything other than the correct type, for example providing a number when a string was annotated, will result in a compile time error. Now TypeScript also supports optional members on classes. Let's look at them with another example. Here we have a class with required members x and y of type number. Now because we haven't provided any default value for these x and y members of type number, nor have we initialized them in the class constructor, TypeScript is going to highlight this as a compiler error. Now we can fix that by initializing these values in the class constructor, or we can provide an initializer inline. Alternatively, now that we understand optional members, we can remove the initializer and simply mark these members as being optional. Now because these members are optional, we can create an instance of the point class, and not provide any initial values to the x and y members, and if we try to read these members, the JavaScript runtime will return us the special value undefined. Once more, TypeScript understands that and automatically adds undefined to the number of possible values for optional members. This means that we can assign it the correct type, which in our case is number, or we can even assign it the special value undefined. Now, one final thing worth mentioning for optional members, be it types or classes, is that null is not considered an optional value. So if we try to assign null to a particular member, it will result in a compile time error. If you want to support null as a possible value for any of the members of your types or classes, you will have to add that as an explicit annotation, for example using a union type. It is entirely possible to end up in a situation where TypeScript's code flow analysis cannot be sure that a value is null or undefined. Let's look at an example. Here we have a type representing a point in two-dimensional space with members x and y of type number. We declare an instance of this point and then create a utility function to initialize this instance. Later on in our code, we initialize this instance and then try to access its x and y members. At this point, you can see that TypeScript is giving us a compile time error. The reason for this error is that TypeScript does not do deep code flow analysis and therefore does not understand the impact of calling the initialize function. Therefore, it assumes that point may or may not be still undefined. And of course, we know that point can no longer be undefined, and we can help TypeScript understand this fact by using a non-null assertion operator. So at any point where TypeScript still thinks that point might be undefined, we use a postfix exclamation mark, and this exclamation mark is what is known as a non-null assertion. Just like other type assertions we have seen before, non-null assertions are compile time only and have no runtime impact. So it is up to you to ensure that the value is indeed not going to be null or undefined. So it is generally better to rewrite your code to avoid these non-null assertions. For example, in this particular case, we can get rid of the dangling variable declaration and then rewrite the initialize function to return us the point, and then only create the variable after the function has been invoked. This ensures that the point variable is always initialized and we no longer need the non-null assertions. Now, non-null assertions can work on any variable or a member of a variable. Let's demonstrate that with another example. Here we have a type representing a person that always has a name but may optionally have an email that can be string or null or undefined. Next, we have a utility function to send an email given an email address, and just as an example, we have a mock implementation that logs out the email to the console. Now, to ensure that a particular person is contactable, we have this utility function that checks if person.email is equal to null or undefined, and in that case, throws an error. Now, if this function ever returns, that ensures that person.email will not be null or undefined, and therefore it must be a string. Now, in order to contact a particular person, we have this function that takes a person, and the first thing it does is ensures that person.email will not be null or undefined by using our utility ensureContactable function. So if this function returns, we should be able to safely invoke sendEmail because we know that person.email must be a string. However, once more, TypeScript has failed to infer this particular side effect of the ensureContactable function and therefore thinks that person.email might still be null or undefined. Now, just like before, we can override this error by using a non-null assertion, that is, putting an exclamation mark after the value that TypeScript thinks might be null or undefined. Also, just like before, it is up to you to ensure the correctness of your code at this point. We can rewrite our code to make it a bit more easier for TypeScript to infer. For example, we can take the assertion from the ensureContactable function and move that inline. This triggers TypeScript's code flow analysis for person.email, and now TypeScript knows that person.email will not be null or undefined and therefore must be a string and will let us safely invoke the sendEmail function. The most common use case of type definitions in TypeScript is to declare the structure of an object. For example, here we have a type representing a point in two-dimensional space with two members x and y of type number. Now we can create a new type to represent a point in three-dimensional space using an intersection type, bringing in all of point 2D and adding the member z of type number. Now, of course, there are various reasons to use a type definition. For example, we can enforce the structure of a variable in our code base. And now, if you make any type errors, for example, forget to assign the z member, we get a nice compile time error from TypeScript. Now, in addition to type aliases, which are created using the type keyword, the same can be achieved in TypeScript using interfaces which are created with the interface keyword. Beyond the keywords type versus interface, the other key syntactic difference is the use of the assignment operator in a type alias. This is because type aliases are simply a way to give names to any possible type annotation syntactically similar to how you would assign a value to a variable in JavaScript. Interfaces, however, operate on body blocks syntactically similar to how you would create a class in JavaScript. Now, for creating point3d in type aliases, we used an intersection type to bring in all of point2d and then add the member z. We can achieve the same effect with TypeScript interfaces by using the extends keyword similar to how you would do it in a JavaScript class. Now, in terms of usages, the type alias and the interface can be used in a similar fashion. For example, we can use the interface to declare a variable of a particular type, just like we did for the type alias. And this provides the same level of safety that we were getting from the type alias. For example, if you forget to provide the member z, we get a nice compile time error from TypeScript. Now, just like type aliases, interfaces in TypeScript only exist for compile time type checking and are not a part of the output JavaScript generated by the compiler. There are two key reasons why interfaces exist in TypeScript. One reason is familiarity for developers coming from other programming languages. For example, they get to use the extends keyword and can create type hierarchies with a more familiar syntax. The other key reason is interface declaration merging, and we will look at that in the next lesson. TypeScript interfaces support a feature called declaration merging. An example use case of that would be something like the Node.js framework called Express. The base request type supported by Express has a few properties, for example, the body property. Now, within our application code, when we handle an Express request, we will have access to any of the properties that are declared on the request type. For example, we have access to this body property. Now, declaration merging allows a middleware, for example a JSON middleware, to add additional properties to the request interface. TypeScript is going to merge the two declarations of the interface into a single type that has both of these properties. So in our code, simply by importing the JSON middleware, you will get access to the JSON property on instances of the request interface. Declaration merging is not something that is supported by type aliases, so if you are working with an API that requires such seamless structural extension, you will have to use an interface. Here we have an interface representing the kind of properties that a UI input element might accept. For example, it has a member type, which can be text or email, a current value for the input element, and a method to handle changes to the value. We can achieve the same effect using a TypeScript type alias. And you can see that the body of the interface has a one-to-one correspondence with what we are assigning when creating the type alias. Now, a great thing about type aliases is that anything you put in a type position can be put as an assignment for a type alias. In fact, TypeScript even offers a refactoring that takes something in a type position and extracts it out to a type alias. So if you wanted, you can break out the onChange handler into a name type. Similarly, you can create a type alias from primitive types like string and reuse it in the onChange handler. And you can even use the type alias for the union of text and email literals. Now, because interfaces must have a body, they do not support these shorthand function syntax or the ability to create interfaces from primitive types. And if you want to give a name to a type union, you will have to use a type alias. Additionally, there are other advanced features like conditional types that we will look at in a future lesson, which are only supported by type aliases. So now let's take a step back and compare the pros and cons. On the left, we have features that are only supported by type aliases, and on the right, we have features that are only supported by interfaces. So if you want any of the features that are shown on the screen right now, the choice will be made for you. But what about the common ground? Well, really the choice is up to you. You can use whichever syntax you are more comfortable with and only use types or interfaces for the specific features that are shown on screen. Personally, my default stance is that I use types unless I need to use interfaces for a particular reason. For example, I'm working with an API that needs declaration merging, or working in a codebase that has deep type hierarchies where extends feels a bit more natural than intersection types. Now, because TypeScript does code flow analysis, there are certain instances where it infers that something can never occur. For example, here's a function that always throws, and therefore it can never return a value, and TypeScript infers its return type to be the special type never. Another example of a function that never returns is something that has a very obvious infinite loop, for example while true. Here, once more, TypeScript infers that the return value of this function is never, as this function will never return. Now, never can also be used as an explicit type annotation in TypeScript. For example, here we have a variable which we have annotated to be never. A key feature of the never type in TypeScript is that only something of type never can be assigned to something of type never. So if we try to assign a number to a variable of type never, TypeScript will give us a compile time error. For example, number cannot be assigned to something that is never. We can use this fact to ensure that all important cases are handled in our codebase. Let's look at an example. Here we have a type square with a member size of type number, and then we have a type rectangle with member widths and heights of type number. Then we have a union type shape that allows us to work with square and rectangles in our utility functions. Now our objective is to create a utility function that returns the area for any given input shape. To ensure that we handle all the types of shapes that might be input, the first thing that we do is create a never variable, ensure all cases are handled, and try to assign the input shape to this variable. Now because the input parameter is of type shape, which is not assignable to something of type never, this will result in a compile time error. Only after we've handled all the cases will S truly become never. So this error is going to force us to handle the different cases, and the first case that we handle is that for the square. Now once this case is there, the error changes that rectangle is not assignable to never. So the next step is to handle the case for rectangle. And now the error goes away, indicating that we have successfully handled all the cases. Now it is a good idea to leave this never assertion as a part of the area function, ensuring code correctness for future modifications. For example, if in the future we decide to support the circle type as a part of our shape, we immediately get a compile time error because circle is not handled within the area function, and the error message is that circle cannot be assigned to never. This helps the person making the modification, and they can ensure that this new type is handled in all the utility functions. Now one final thing worth mentioning is that all parts of a function must return a value, otherwise TypeScript infers that the return type of the function might be undefined. For this particular case, we can simply return the ensure variable, and now TypeScript correctly infers that the return type of the function will be a number. We have a type representing animals with a property name and a method voice. Now we can create utility functions that work on top of animals. For example, here we have a log function that logs out the animal's name and voice. Now we want to be able to use these utility functions on instances of classes cat and dog. Now TypeScript can help ensure that cat and dog provide all the features required by an animal by using an implements keyword. So we specify that class cat implements animal. And as soon as we do that, we get an error from TypeScript. The error message tells us that at this point, cat is missing the following members required by animal. It is missing a name and a voice. Adding an implements animal annotation is helping us ensure that we provide all the features that are required by an animal type. And now we can provide the features that are highlighted, for example, create a name parameter property and then provide the voice method. And now we can repeat the same process for the dog class, adding implements animal, noticing the error message, and then providing the members that are highlighted by the error message. And now, since no errors are being highlighted by implements animal, we can rest assured that instances of cat and dog can be used at any place where an animal is required. Here we have a variable representing the value of a dice of type number. Then we have a utility function rollDice, which updates the value of the dice with a new random value. To ensure that dice is always a valid number, we do an initial roll of the dice. Now at this point, if we try to read the value of the dice, we get a compiler error from TypeScript. The error message indicates that variable dice is being used before it has been assigned. The source of this error is the fact that we are not doing a direct assignment of the variable at the point of declaration and only doing one later on through a function call. Since TypeScript doesn't track the mutating side effects of a function, it thinks that dice might still be undefined. We can overcome this error with a non-null assertion, as we have seen in a previous lesson. It does get rid of the error. However, if we try to roll the dice again and then read its value, TypeScript still thinks that dice might be undefined, as it has still never been initialized directly. So let's get rid of our non-null assertion and look at an alternative fix. We can use an exclamation mark after the variable name at the point of declaration to tell TypeScript that this variable is definitely assigned. This exclamation mark at the point of declaration is known as a definite assignment assertion. And now TypeScript no longer complains that the variable is used before assignment. Just like other assertions, the definite assignment assertion is compile time only, and it is up to you to ensure correctness. Now definite assignment can also be used with members of a class, so let's look at another example. Here we have a class representing a point in two-dimensional space with members x and y that we initialize to random values in the constructor. This class also provides a utility method to reinitialize the x and y members to new random values. At this point, you can see the code duplication between the constructor and the moveRandom method. We can get rid of this duplication by simply invoking the moveRandom method from the constructor. However, this raises a compiler error for the members x and y, and if you look at the error message, you can see that it is complaining that the members x and y do not have an initializer and are not assigned to a value in the constructor. This is similar to the error message we saw in our previous example, and the cause once more is the redirection introduced by the function call. The fix is once more the same, that is, we do a definite assignment assertion by adding an exclamation mark after the member declarations. Here we have a type representing a square with a member size and a type rectangle with the member's width and height. Then we have a type shape which can accommodate both squares and rectangles. In our utility function area, in order to discriminate between the square and the rectangle, we check if it has a member size to determine if it's a square, and we check if it has a member width to determine if it's a rectangle. Now these conditions are not explicitly clear that we're checking if something is a square or a rectangle. We've discussed before how we can improve the situation by adding a common member between square and rectangle of different literal types, thus forming a discriminated union. However, if we do not want to modify the types themselves, we can still get the readability benefits by creating user-defined type cards. We start off by copying this condition into a utility function called isSquare. Notice that this function returns a Boolean value. A user-defined type card is simply a function that returns a Boolean value and is annotated in the form parameter is type. For example, here we have the parameter as shape and the type as square. Here we are communicating with TypeScript and telling it that if this function returns true, this means that shape is of type square. Now in terms of type inference, these user-defined type cards behave exactly the same as the built-in type cards offered by JavaScript, for example, the in operator. So we can replace the condition in our if block with a call to our user-defined type card. And now TypeScript understands that within the block, this means that shape must be a square. And now we can repeat the process for the rectangle type, creating a function isRectangle that is annotated to return shape is rectangle, and then internally simply checks if width is present in the input shape. And now we can replace our property check type card with a much more meaningfully named function call. Here we have a type representing a person with a member name of type string and an optional member date of birth of type date. Now within the JavaScript ecosystem, it is common to have a function that asserts that a particular condition is true. So if the condition turns out to be false, it throws an error instead of doing a standard return. Let's look at an example where we might use such a function. Here we are loading the person from a network call. Now if the network call fails, our loadPerson utility function returns null. And this can be seen in the type inferred for the maybePerson variable. So before we try to use this person object, we use our utility assertion function to assert that maybe person is not equal to null. Now from our understanding of this function, we know that if this function returns, we should be able to access any of the properties of the person, for example, the name property. However, if we do so, we get a compiler error. If you hover over the error, you can see that TypeScript still thinks that maybe person might be null. Now the reason for this error is that TypeScript does not do any implicit assertion checking. However, it does support explicit assertion checking in the form of assertion functions. To specify that a particular function is an assertion function, we need to add a return type annotation of the form asserts some parameter. Here the parameter we want to assert is called condition. This tells the TypeScript compiler that this function only returns if the condition parameter is true. Functions with such a return type annotation are called assertion functions. Now that TypeScript understands the impact of calling this function, it knows that maybe person not equal to null must have been true, and therefore maybe person can only be of type person. In addition to assertion functions that simply assert if a passed-in parameter is true, you can create an assertion function to indicate that a passed-in parameter is of a particular type. Here we have a utility function which asserts that a passed-in parameter is of type date. If the value is an instance of date, it simply returns. Otherwise, instead of doing a return, it throws an error. Now at this point, it is not an assertion function as we haven't added an asserts annotation. But let's demonstrate its intended usage before we add a proper annotation. Now we want to read the date of birth of the person, so we use this assert date function to ensure that date of birth is of type date. Now we know that if this function returns, we should be able to access the date of birth as the type of date, for example, invoke its toISOString method. However, without a proper type annotation, we immediately get a compiler error, and if you hover over the error message, you can see that TypeScript still thinks that date of birth can be undefined. The syntax for specifying that a function asserts a particular parameter to be of some type is asserts parameter name is type. Here we are saying that the assertDate function only returns if the passed-in parameter value is of type date. With this annotation in place, TypeScript successfully narrows the date of birth to be of type date, allowing us to call the toISOString method. As a final thought, you might have noticed that the syntax for assertion functions is very similar to the syntax for user-defined type cards. And you might be wondering when you should use an assertion function and when you should use a user-defined type card. Normally in your application code, you would use a user-defined type card as you do not want to be throwing errors in your application code. However, when writing application tests, you would use an assertion function as unhandled errors are gracefully reported as a test failure by popular testing frameworks. Here we have a function called reverse that can be called with a string or a string array, and if it is a string, then it splits the string into its characters, reverses them, and then finally joins them back to return the reversed string. Alternatively, if it is invoked with a string array, it creates a copy of the array using slice and returns the reversed version of that array. So if we invoke this function with the string hello, we get the reversed string uleh. And similarly, if we invoke it with an array of characters, we get back a reversed array of characters. Now we know that if the input is a string, then the output of the function is a string, and if the input is a string array, then the output is a string array. However, as far as the inference engine in TypeScript is concerned, there are two possible ways that the function can return. It can either return a string, or it can return a string array, and TypeScript infers the return type of the function to be a string or string array. So if we hover over the first variable, you can see that TypeScript thinks that it might be a string or a string array, and the same is true for the second variable. Now the solution to this problem is function overloading. We can declare multiple signatures for any given function before the function body. So we declare a function signature such that it takes an input string and it outputs a string, and another signature specifying that when it takes a string array, it returns a string array. Now with these two function overloads in place, TypeScript knows that when this function is invoked with a string, it returns a string and infers that correctly for the first function call. Similarly, it correctly infers a string array for the second function call. Now function overloading in TypeScript is compile time only. That is, these signatures are not a part of the output JavaScript. This is why we are only allowed to have one body for the function which must handle all the overload cases. For example, here we are using a type of check to determine which code block we want to execute. Additionally, adding overloads shadows the internal function signature, so let's look at another example to demonstrate that. Here we have a function called makeDate designed to help us make date objects. Within the function, we check if a month and day were passed in, and in that case we assume that the arguments are the year, the month, and the day. Otherwise, we assume that the first argument is the timestamp, that is the time in milliseconds since epoch. So we can create an instance of the date using the makeDate function, passing in the year 2000, month Jan, and day first. Similarly, we can create a date by passing in the time since epoch, and let's just pass in 0 to create the date of epoch. Now, if someone were to look at just the function signature, they very well might assume that you should be able to pass in just the year and the month. However, when we look at the code, you can see that if day is not passed in, then the second code block will execute, and in that case, the month argument will be completely ignored, and the year argument will actually be thought of as a timestamp in milliseconds. However, with the single function signature that we have right now, we are able to invoke the makeDate function with 2 arguments. Once more, the solution to this problem is to declare function overloads. So we create a function overload where we accept a timestamp of type number and specify that we will return a date, and then another function signature where we specify that we will take 3 arguments, which is year, month, and day, and then return the date. Now when we declare the overloads, it essentially shadows the internal function signature, and now externally there are only 2 possible ways to invoke the function, one with the timestamp and one with year, month, day. So now TypeScript is correctly highlighting the fact that you cannot invoke the makeDate function with just 2 arguments, and we can get rid of this incorrect function call. So now you might be wondering why we need to have an implementation signature when it is not visible to consumers of our API. Well, the reason is that the implementation signature is there only for the author of the function to declare how they would like to handle all of the possible cases declared by the overloads. This is the only function signature that is visible within the body of the function. Here we have a type add representing a function that can be invoked with 2 parameters, each of type number, and then returns a number result. We can use this type in any type annotation position. For example, here we are declaring a variable to be of this type. Now this shorthand syntax for declaring the type of a function can be used inline, or as we have done in this case, assigned to a type alias. Another way of declaring the type of a function is by using call signatures in a body block. So we paste what we have in the shorthand syntax, and the only modification we need to make is replace the arrow with a colon, similar to how you would annotate the return type of a function. As far as TypeScript is concerned, this type is exactly the same as what we had in the shorthand syntax. This body block syntax is also what you would use to declare the type of a function if you wanted to use an interface instead of a type alias. Of course, these are both equivalent, other than the fact that an interface is open for declaration merging. Let's swap back to a type alias. Now using a body block means that you can also add other members, for example an optional debug name property to the type add. And now this property is available for access on our variable. Another feature available in this long form is the ability to declare function overloads. Here we are saying that the add function can also be invoked with 3 parameters. And now we update our implementation to accept the third optional parameter as well as use it if it is provided. In addition to simple functions, TypeScript also supports providing the type annotation for a function that is invoked with the new operator, also known as JavaScript classes. Let's look at an example. Here we have a class called point with 2 members x and y of type number. Now classes in JavaScript are an expression that can be assigned to any variable, for example a variable called point. Now we can declare the type of such a variable by using the familiar syntax from call signature. The difference is we precede the call with new, and for the return type annotation we provide the list of members that will exist on instances of the class. And now we can use this type annotation for our point variable. Now just like for functions, this constructor signature is the short form. There is an equivalent long form syntax as well. So within our parentheses, we paste in the same short form, and the only thing we need to change is change the arrow to the return type annotation just like we did for simple call signatures. As a final note, let's combine everything we have learned into a single type annotation. Here we have a type with multiple constructor overloads, as well as function overloads, as well as a property called the bug name. And although you are very unlikely to create a type like this, at least you can appreciate that types in TypeScript are extremely expressive. TypeScript allows you to create abstract classes, a concept that you might be familiar with from other programming languages. A class can be marked as abstract by using the abstract keyword, and then you get the ability to provide abstract members. For example, here we have an abstract method called command line. Now the abstract members do not have any implementation, and the whole objective of an abstract class is for it to be inherited and then for the child classes to provide an implementation for these abstract members. This means that within other portions of our abstract class, we get to assume that these members will be provided. Here we have a dummy execute function that simply logs the command line to the console, but in a more real-world scenario, it might spawn up an actual terminal process. So this abstract command class takes a particular command line from its child classes and then provides the reusable functionality to execute that command line. So the main consumers of an abstract class are classes that want to extend it. Here we create a class called getResetCommand that extends this command. Now as soon as we extend the base abstract class, we get a compiler error, and if you look at the compiler error message, you can see that it is complaining that the child class does not provide the functionality required by the abstract class, which is the command line method. So we go ahead and provide the command line, and now we get the execute method for free. We can repeat the process for as many commands as you want, for example, the git fetch command. So now we can create instances of the git reset command and the git fetch command and call their execute methods. Now one final thing worth mentioning that might be obvious is that you cannot create instances of an abstract class by itself. The obvious reason is that an abstract class has abstract, that is missing, features. For example, here the command line method would be missing. Here we have a JavaScript object with a single member hello. You can access members of a JavaScript object using a string index. Similarly, here we have an object with the single member 1337. We can access this member using a number index, similar to how you would do it in a JavaScript array. TypeScript allows you to access members of a JavaScript object using arbitrary string or number indexes by declaring an index signature. Here we are declaring a type whose instances you will be able to access using a key of type string, and the members will be booleans. The type for the key can only be a string or a number, as those are the only ones that are safely supported by JavaScript. You are free to name the index member whatever you want. It is only used for developer documentation. Here we've simply used the name key. And in terms of values, you can put whatever you want. Here we've simply used the type boolean. Now let's look at an example application of an index signature. Here we have a type representing a person with members display name and email. We can declare a type for a key value pair of username to persons using an index signature. We can create an instance of this dictionary as a simple JavaScript object. Here we've pre-initialized it with a single key called Jane and a corresponding person object. We can also assign to any given key afterwards. For example, here we are assigning a person to the key John. We can also read the value at any given key using a JavaScript string indexer. Additionally, we can use the JavaScript delete operator to delete the value at any given string index. You are allowed to mix index signatures with other well-defined members. For example, here we are saying that the person dictionary must always have a member Jane of type person. So if we try to create a person dictionary without this member, TypeScript will give us a compile time error. And if we get rid of this required member, the error will go away. Also, all additional members of a type with an indexer must conform to the index signature. For example, if we try to create a member Alfred of type boolean, TypeScript will complain that boolean is not assignable to the index signature, which is person. So we can either change it to be of type person or just get rid of this member. Now you can always access this person dictionary with any given key. However, if the key value is not present, the JavaScript runtime will return us the special value undefined. And accessing something like an email off of an undefined will result in a runtime error. However, notice that TypeScript is not catching this right now. If you want TypeScript to catch these mistakes, you can add a union of undefined to the values returned by the index signature. And now TypeScript correctly highlights a potential error with the familiar message object is possibly undefined. Now, one more thing worth mentioning is that when we are assigning by a given string index, TypeScript is still going to provide us with type safety to ensure that it is actually a person. For example, here we've made a typo in the email member, and TypeScript has figured this out and provides a suggestion for the correct spelling of email. Here we have a JavaScript function that takes an input array and then invokes sort and reverse to return a reverse sorted array. We create an array of 5 numbers stored in a start variable. Then we invoke this reverse sorted function and then store the result in a result variable. Now at this point, our result is exactly what we expected it to be. It is the 5 numbers in reverse sorted order. However, sadly, the reverse sorted function has also mutated our input array. This is a very common mistake to make when beginning JavaScript development, and the reason is that the sort and the reverse methods, in addition to returning their results, also mutate the original array. Fortunately, with TypeScript, instead of declaring the input as a number array, we can declare it as a read-only number array. And now any mutating methods will no longer be available on input. So if we want to use the sort and the reverse methods, the first thing that we will need to do is to create a copy of the input array using the built-in slice method. This creates a new non-read-only array which can then be safely sorted and reversed and then returned. And now when we invoke this reverse sorted method on the start variable, the start variable is no longer mutated, which is very cool. Now you might remember that for JavaScript arrays, TypeScript has a neat syntax which we prefer, as well as a more verbose array generic syntax. The same is true for read-only arrays. We prefer the neat syntax as you saw us already use that for the input parameter, but there is an equivalent read-only array generic interface. Now TypeScript also supports read-only tuples, and we've mentioned this before that tuples are simply arrays with fixed lengths, so let's look at a tuple example. Here we have a tuple representing a point in two-dimensional space with 2 members, both of type number. We create this utility move function that accepts a given point and the distance to move in the x and y dimensions, and then updates the values in the input tuple and then returns the modified tuple. So if we create a point with x and y 0 and move it by amount 10 and 10 in the x and y dimensions, we do get the moved point with 10, 10. However, this results in a side effect of mutating our input point also to 10, 10, which makes us sad. Now just like arrays, we can annotate a tuple as read-only by using the read-only modifier before the tuple declaration. And now any attempts to modify any given point will result in a compiler error. For example, here you can see that we cannot mutate the y value. So now we can fix this error by replacing our mutating implementation with an implementation that returns a new tuple created from the existing tuple plus the moves in the x and y dimensions. So now when we invoke the move method on an existing point, we no longer mutate the original point, which replaces our sad tears with tears of joy. Here we have a type point2d with members x and y of type number, and a type point3d with members x, y, and z of type number. And then we have a type person with a name in an email. Then we create variables of each of these 3 types, so we can do some type comparison between them. Remember that types in TypeScript are structural. This means that we can assign a point 3d to a point 2d without any errors, because a point 3d does have all the members that are required by a point 2d, which is x and y. However, we cannot assign a point 2d to a point 3d because a point 3d requires a member z, and this variable point 2 simply does not have that. However, we can force this assignment to happen by using a type assertion. Here we are saying that, dear TypeScript, I know you think this is a point 2d, but trust me, it is a point 3d. And TypeScript, being a nice companion, happily agrees with you and trusts you completely. However, this single assertion is sometimes not enough. Let's look at an example. We know that a point 3 cannot be assigned to a person as there are no common members between them. The same is true that we cannot assign a person to a point 3. Because of this bidirectional incompatibility, if we try to assign a person to a point 3, even with a single assertion, TypeScript will still complain. And if you hover over the error message, you can see that TypeScript is saying that this is probably a mistake, but if you still want to do something like this, then add an additional assertion to unknown. And if we do this process of first asserting to unknown and then asserting to point 3D, indeed, TypeScript trusts us and does not check us with any errors. Now from our lesson on unknown, we can understand why this is working. Unknown is allowed at least one-way compatibility with all types. That is, a variable of all types can be assigned to a variable of type unknown. So anything can be assigned to unknown, for example a person, and an unknown can be asserted as anything, for example a point 3D. So that is how a double assertion works, and it goes without saying, use it with caution and avoid it as much as possible, but it might help you migrate some JavaScript code. Here we have a JavaScript utility method that is designed to double the value member of any given this. Now you might be familiar that this is known as the calling context in JavaScript. It is an object that is implicitly passed into the function by the JavaScript runtime, depending upon how the function is invoked. Let's look at an example how we might use such a function. Here we are creating a JavaScript object with two members, a value member pointing to the number 10 and a double member pointing to our utility function. So if you go ahead and invoke the double method on this JavaScript object, the JavaScript runtime will take this object and pass that into the function as this. So within the function body, valid.value will be changed to valid.value *2. So after the function invocation is complete, valid.value will now be 20. Now even though this works, we haven't actually annotated what this needs to be within the double function, and therefore it is not being enforced to any particular type by TypeScript. So if you were to have an object where we misspell the value member, for example here we've misspelled it as valve, and then try to invoke the double method, it will result in undesirable runtime behavior. However, we do not get any error from TypeScript. Now TypeScript supports annotating what this should be within a particular function by using a this parameter. Here we are saying that within the double function, this should be treated as something that has a member value of type number. This type is enforced within the function body and also enforced when trying to invoke the double function. So when we try to invoke it on something that has a value member, TypeScript allows it. However, if you try to invoke it on something that does not have the value member, for example our invalid object, TypeScript gives us a compile time error. If you look at the error message, you can see that TypeScript is complaining that value is missing on this particular object. However, it is required to be present in order to invoke the double function. So now we can get rid of the error quite easily by fixing the typo in our value member. Now there is one more thing to note about this parameter. It must be the first parameter within the function declaration. The reason is that this parameter is a fake parameter, that is, it is not a part of the generated JavaScript and only used for compile time checking. This is implicitly passed into the function by the JavaScript runtime and therefore does not need to be a part of the generated JavaScript. Here we have a generic function that takes an object of type t and then returns the same object. At this point, this function is a simple identity function. We can modify this function to return a shallow clone of the passed-in object. Here we are returning a new object and using the JavaScript spread operator to spread all the members of obj into the new one. In addition to returning all the members from obj, we can add an additional member called full name of type string. So we add that to the return type annotation and then provide a default value for the full name member in the return object. Now the purpose of the add full name function is actually to generate a full name property by using the obj first name and the obj last name. At this point, TypeScript is complaining that it does not know what is intended by obj first name and obj last name, as these members are not declared anywhere. In order to access these members from the obj of type t, we have to declare that the passed-in obj must conform to a particular structure, and that is done by using a generic constraint. Here we are saying that type t must have all the members that are present in the type name fields. Of course, we could declare this type inline, but let's just create a type alias to keep our code a bit clean. Now with this generic constraint in place, TypeScript will ensure that the object of type t has the members first name and last name of type string. Now let's demonstrate a usage of this function. So we invoke this function with an object that has a member email, a first name and a last name, all of type string. Now because of the function signature where it takes a t and returns a t, we are able to access any of the members of the originally passed-in object, for example, the email field. In addition, in our return type annotation, we say that the return object will get this property full name of type string, and indeed we can access that on the returned John object. Now the generic constraint extends name fields is allowing us to access the first name and the last name property within the function body. Additionally, it is enforcing that the passed-in object should have these members first name and last name of type string. Let's look at an example where we fail to provide these members which are being enforced by the generic constraint. TypeScript immediately reports this as an error, and if you look at the error message, it is telling you that the last name property is missing in this object that is being passed into add full name. Armed with this information, we can provide the last name for Jane, which in our case is Austin, and now the error goes away because everything is fine. Here we have a variable called center with members x and y initialized to 0, representing the center of a two-dimensional plane. Later on in our codebase, we create a unit variable based off of the center offset by 1 in x and y. Our application is complete and we deploy to production. Then we decide that we want to support 3 dimensions and add the member z to our center variable. At this point, we realize that our code would be much more maintainable if we had types in our codebase. Now we can create a type for points in our codebase and specify that they need to have 3 members x, y, and z. However, realize that TypeScript already knows the type of center from its initializer, and it understands that it has 3 members x, y, and z of type number. This is exactly the same as the type we just hand-coded. Well, fortunately, TypeScript provides the type of type operator to generate a type from any variable in your codebase. This type will be the same as whatever TypeScript inferred for the center variable. In our case, this is exactly what we wanted, and you can see that by hovering over the type alias. So now we get to use this type without ever having to code it by hand. Of course, if it was a bigger variable, it would be a bigger time saving. And now you can see that TypeScript is complaining that z member is missing for the unit variable, so we go ahead and provide that. Now, even though we use the type of operator to create a type alias, you can use this inline as well if you wanted to. Now let's look at another use case of the TypeScript type of operator. Here we have a sample JSON response that we've saved from a network call. Of course, JSON is valid JavaScript, so we can jump into our TypeScript source code, create a variable to store this response, and then paste that in. And now instead of having to hand code the type of the API response, we can let TypeScript infer that from this variable and even create a type alias from it. And now we can use this type in our codebase. Whenever we get an API response, we simply annotate it as %response and use its various members. For example, here we're logging out the full name as the first name plus last name. I once worked on an application where the backend needed a bunch of information specified by a type called submitRequest, similar to what is shown over here. Then different portions of the UI would collect portions of this request and send it back to the backend. For example, a portion of the UI was dedicated to the purpose of collecting the credit card token. Now, in order to ensure consistency between the return type of the getPayment method and the payment portion of the submit request, we could extract that portion out into its own name type, for example, payment request, and then export that from the common library and then use it in our UI application. But this leads to 2 problems. First, we need to start asking the backend team to make modifications to their type definitions, and additionally, we will probably start asking that for other portions of the submit request as well. A second issue with this approach is that now for someone looking at just a submit request, they would see various members pointing to different types, and it would not be immediately clear to them why these types need to be split out. These additional types are essentially type noise in the common library. The solution to both of these problems is provided by TypeScript's lookup types. So we get rid of the return type annotation, get rid of this extra type within our common library, and then revert submit request to all be inline. Now using TypeScript's lookup types, we can look up the type of the payment member from submit request on the fly. The syntax for looking up the type of a particular member is similar to the syntax of looking up a member from a JavaScript object. Here we are saying that the return type of the getPayment method should be the same as the type of the payment member of submit request. This return type annotation ensures that we return the correct type and if you make any silly typos, for example add an extra s, you can see that TypeScript points it out as a mistake. Now we have used this lookup type in line, but if you find yourself using the same type again and again, you are still free to create a type alias using a lookup type. This is still better than our previous solution because a submit request is still one cohesive type, and additionally this particular utility type can live in our UI project and not in the common library. Now lookup types can also be used to look up the type of the items in an array. Within our type submit request, we have a member personal that has the member previous aliases, which is an array of items as indicated by these square brackets. So a previous alias is something that has three members: first name, middle name, and last name. Let's see how we can get that type. So we jump back to the UI portion of our code, and the first thing that we will do is that from submit request, we look up the member personal, and then from the type submit request personal, we look up the member previous aliases. As we saw before, this particular member is an array. So to get the type of the items in the array, all we need to do is to look up the first item by using an index 0. And now our previous alias request is exactly what we wanted, that is a type with three members: first name, middle name, and last name. Here we have a type representing a person with members name and location of type string and age of type number. We have an example of such a person in the form of John, aged 35, living in Melbourne. We have a utility function that lets us access any member of John along with logging out a statement to the console. As an example, we can use this method to get John's age. Now an issue with the signature of our logget function is that it allows any old string key to be passed in. For example, we can pass in a key that is not present on the John object, like email. Now we can improve the situation by replacing our open-ended string with a limited set of string literals using a string literal union. For example, we can say that key must be name, age, or location, which are the only valid keys for the person type. And now TypeScript correctly highlights invalid access as an error. However, this list of keys is essentially code duplication that will have to be maintained as we continue to work on the person type. Fortunately, this is something that can be automated with the TypeScript key of type operator. The key of type operator takes a type as input and returns a union of the keys from that type. And this is exactly the union of the strings that we wanted. So we can replace our hand-coded union of string literals with a simple key of query on the person type. And because we are restricting the keys to be from the person type, we'll annotate the obj to be of type person as well. Now notice that our logget function doesn't have any code specific to the person type. To make this function more general, we can use generics using a generic type for the obj and a generic type for the key. And now the requirement that key must be something that is in the key of obj can be enforced by a generic constraint when we define the generic argument. Now with this generic constraint, TypeScript knows that key will be something that is in the key of obj. So when we try to index obj with key in our JavaScript code, TypeScript correctly infers the type of the returned value to be an index lookup type obj key. And since value is what we return from the logget function, the return type of the function is also inferred to be the lookup type obj key. Now with this function signature in place, when obj is of type person and key is of type age, the return type will be the lookup person age, and we can see that it needs to be a number. And indeed, that is what is automatically inferred when we try to use logget to get John's age. And now we can get rid of the invalid access for the email property. Now similar to how we have the logget function, we can easily apply the same knowledge to build a logset function. The body of the function is pretty simple. In terms of the function's signature, it is very similar to the signature of the logget function. The only difference is that the logset function takes an additional third argument, which has been annotated with a lookup type obj key. And we've seen this type before as well. This is exactly the return type of the logget function. And now we get a nice utility function that can be used to set any value on a member of any type. And if you make any silly mistakes, for example, misspell a property or provide an invalid type for that particular property, we get a nice compiler error from TypeScript. Now the key of operator by itself is quite simple. It simply returns the union of strings of keys of any given type. Here we've combined the key of operator with other features in TypeScript, which are generics, generic constraints, as well as with lookup types to provide type safety for something that can be used to observe any given object. Conditional types in TypeScript allow you to create conditional logic functions within the type system. Let's look at an example. Here we have a generic type is number. It takes the type as a generic input, stores it in type T, and then checks if type T extends the type number, and if that condition is true, returns the literal type number, otherwise returns the literal type other. These types are called conditional types because of the use of the conditional operator. This is modeled after the conditional operator within JavaScript. People often also call this the ternary operator because this is the only operator within JavaScript that has three inputs: a condition, a result when the condition is true, and a result when the condition is false. Now our isNumber utility function over here can be invoked with any JavaScript value. For example, it can be invoked with a number or it can be invoked with a string. The same is true of our isNumber type function. It can be invoked by passing in a generic for the type T. For example, we can pass in a number as type T, or we can pass in something else like a string. The logic for these types is run within the TypeScript type system. When the type number is passed in for T, TypeScript sees that number extends number, it understands that to be true, and returns the literal type number. And we can see that when we hover over the result. Similarly, when the type string is passed in for T, TypeScript sees string extends number, it understands that to be false, and returns the literal type other. And we can see that when we hover over the result. This comparison between JavaScript and TypeScript gives you a mental model of how to think about conditional types. The key difference is that while the JavaScript is executed by the JavaScript runtime and works with runtime values, the type function is executed by the TypeScript compiler at compile time and works with TypeScript types. Now let's look at a use case of conditional types. Here we have a TypeScript conditional type that works with all of the types that are supported by the JavaScript type of operator. We can use this conditional type as the return type of a generic function. Within the function body, we simply return the result of the JavaScript type of operator. Our type name T is modeling at compile time what the JavaScript type of T will do at runtime. Let's invoke this function with all of the primitives that the JavaScript runtime supports. For all of these cases, TypeScript will correctly infer at compile time what the return value will be at runtime. For example, when it is invoked with a value undefined, the JavaScript runtime returns type of undefined, which will be the literal string undefined. And we've correctly inferred that if we hover over the result. The same is true for other invocations as well. We've successfully inferred at compile time the runtime return result of all of these function calls. Let's walk through this Boolean example. When we invoke typename with the literal true, TypeScript infers the type of the input argument to be Boolean, and therefore T is Boolean. Now the return type is annotated to be typename of Boolean. TypeScript goes through the conditional type, and the only condition that matches is T extends Boolean, and therefore TypeScript infers the return type to be the literal Boolean. And we can see that inference when we hover over the result. Now one thing that you might find surprising is that the inferred result of invoking the function with null is the literal type object. And no, this is not a bug, this is just how the JavaScript runtime works with type of null. It actually returns the string object. But fortunately with TypeScript, our typename function can be better than the built-in type of operator in JavaScript. First, we add an additional condition to the typename conditional type to check if T extends null and return the literal null. And then within our runType typename function, we add a condition to check if T is null to return the literal null. And with these two changes in place, our runtime result will be null, and it is also inferred correctly at compile time. Now we can easily keep on adding other conditions to the conditional type and to our runtime function to make a typename utility that is specific to our project and meets our needs more than the built-in JavaScript runtime support. Here we have a conditional type that checks if the input generic extends an array, and if so, it returns the literal type array, otherwise it returns the literal type other. So if we input something that is an array like a string array, we get back the literal array. Otherwise, if we input something like a number, we get the literal other. Now if we continue our mental model of thinking of conditional types as little type functions, the infer keyword can be thought of as a way to create variables within the function. So the inputs of the type function are types and the outputs of the type function are types. Of course, the variables will also be types. For example, we can create a variable out of the type of the array using the infer keyword and giving that variable a name, for example, member. And now this variable member becomes available for access if the condition is true. Let's look at an example where we might want to create a variable within a conditional type. Here we have a type that can be used to unbox the members of an array. It checks if the input type extends an array, and if so, infers the members of the array, and that is what is returned by the conditional type. Otherwise, it simply returns whatever type was input into the condition. Let's look at a few examples where we use this type. If we input string array, it does extend an array and the member is inferred to be string, and that is what is returned. If we input a number array, the same thing happens, and in this case, the member number is returned. For anything else, like just the string type, it returns it back as it is. Now let's add some JavaScript to look at a more practical use case of using conditional types with the infer keyword. Here we have a utility function that accepts two parameters, first name and last name. And then it returns an object containing three properties, first name, last name, and full name. We have another function in our codebase that is designed to log a person, and a person is anything that has been created from this createPerson utility function. Now of course at this point we could create an explicit type to annotate what a person should be, but if you hover over the createPerson function, you can see that TypeScript already knows what a person should be as the inferred return type of this function. So if we could infer the return type of this function, we wouldn't need to create the person type explicitly. So we create the conditional type return type that takes an argument of type t and checks if t extends a function. If it does extend a function, we infer the return value to be r, and that is what we return. Otherwise, we assume that the programmer has probably made an error passing in something that does not extend a function, and we return the special TypeScript type never. And now that we have this utility return type, we can invoke it on the type of createPerson. The type of operator returns the type inferred for the createPerson function, and then our return type utility infers the return annotation. So if you hover over the person alias, you can see that it is exactly what we wanted. And now we can use it to annotate our logPerson function. Now you might be thinking that that was a lot of work for very little gain. Well, the good news is that we don't need to create this return type ourselves, as it already ships as a part of the TypeScript compiler. Similarly, we don't need to create a type alias, we can actually do it just inline. And now if you ever end up in a situation where the input of one function depends upon the output of another function, you can actually generate the type on the fly. And if the output of the first function ever changes, you get a nice compiler error from TypeScript, and you can go ahead and fix that. Here we have a type called point with three members x, y, and z of type number. We will have lots of points in our application, and one such point is the special variable called center. The reason why center is a bit special is because we want this to be immutable. We don't want anybody changing its x, y, or z values. So if anyone tries to assign some value to center.x, we want this to be a compiler error. Now we can achieve that quite easily by creating this type called read-only-point, which has the same members as point, except that all of those members are marked as read-only, and then use this type specifically for the center variable. And now we get a nice error if anybody tries to assign to these members, for example the x member. However, notice the code duplication between point and read-only-point. We can get rid of this duplication by using mapped types. A map type consists of three key portions: a loop variable, a union of types that we are going to loop over, and an output type. In our case, we can loop over the union of keys x, y, and z. And for the output, We know that all of these members need to be of type number, so we use the type number. We don't have the need for a loop variable yet, so we leave it as it is. And with that, you've successfully created your first mapped type. Now right now, this read-only point is exactly the same as the type point. The great thing about map types is that you can add modifiers that will apply to all the loop items. So if we apply the modifier read-only, all of these members become read-only, which is the type that we want to generate. Now let's apply other features from TypeScript to clean this code up a bit more. Instead of hand coding this union of strings, we can generate it by applying the key-of operator to the point type. Additionally, instead of assuming that all of these members need to be of type number, we can read the type of the individual members by using the loop variable to look up the type of the member from point. As a final step, we can create a utility type function by taking a generic argument of type t and using that instead of the hard-coded point type. And now we can use it to create read-only versions of any input type, and for our particular case, our input type will be the type point. And at this juncture, I'm actually happy to inform you that you don't need to create this particular read-only utility type. It comes baked in as a part of the TypeScript compiler, and if we delete our custom implementation, it falls back to that one, and the internal implementation has been coded up exactly how we did it right now. Now with this annotation in place, TypeScript correctly points out any invalid usages of center, and we can go ahead and fix those. Here we have a type with properties of mixed modifiers. We have type X as read-only and type Y as optional. To demonstrate the usage of map type modifiers, we create this utility map type that does nothing other than map over the properties in T and simply map them out to whatever they are within the type T. So if we use this utility type on the type point, the output would be the same as the input. That is the same two members, X as read-only and Y as optional. Now we've already looked at how we can make the properties as read-only in the output type by using the read-only modifier. This makes all the properties as read-only, and you can see that Y has become read-only in the output type. TypeScript also allows you to optionally add the plus sign before the read-only modifier. The output will be the same as without the plus token, but it might help you read better. TypeScript also allows you to add the optional nature in the generated properties by using the question mark token. And now if you look at the generated type, you can see that X has become optional in the output results. Now just like the read-only modifier, you can add a plus before the question mark token if it helps you read better. I personally do not use these plus tokens. However, the reason why they're supported is that you can actually use a minus token to remove the optional nature or the read-only nature. So if we use minus question mark, you can see that the optional nature of Y is removed in the generated type. Similarly, if we use minus read-only, the read-only nature of X will be removed in the generated type. Now to get more experience with map type modifiers, let's look at a use case. Here we have a class designed to manage some state. It takes an initial state and stores it in its current property, and a method update to update the current value with the next state object that is passed in. We can create a new state object with members X and Y initialized to 0. This makes type T for the state instance as X and Y of type number. So we can update the state to a new X and Y value by passing an object to the update method. And indeed, this does update the current state with the correct values. However, notice the implementation of the update method. If we provide an object that doesn't have all the members that are required by type T, it does automatically fill them from the current object. So we should be able to provide just the members that we want to update. However, this results in a compile time error because next has been annotated to accept the full type T and we are not providing the X member anymore. The solution to this problem is to generate a type such that it has the same members as type T, but all of them are marked optional. Now we can create a utility type function called partial that simply maps over an input type T and adds the question mark modifier to all of the members. And now we can annotate the next argument for the update function to be a partial of type T. With this type annotation in place, the error on the update call goes away. Now creating a partial for any given input type is actually a common enough use case that we don't have to code up this particular utility type ourselves. If we go ahead and delete our implementation, it falls back to a built-in implementation provided by the TypeScript compiler that achieves the same purpose. And if you hover over the type, you can see that it is implemented by the TypeScript team exactly how we wrote it right now. Modern JavaScript allows you to create a variable as a const declaration. Of course, we can use type annotations with const declarations. For example, here we have a type point with members x and y, and we can annotate this point variable to be of type point. This ensures that any mistakes we make during the initialization of the variable are caught at compile time. For example, a typo in the x property. Now, the key difference between a const declaration and a let declaration in JavaScript is that you cannot reassign a variable that has been declared with const. For example, if we try to reassign with the equals operator a new object to the point variable, we get a compile time error from TypeScript. Of course, this is because reassigning to a const would blow up at runtime in JavaScript. Beyond this reassignability protection, there are no other guarantees offered by a JavaScript const declaration. For example, we can still go ahead and modify the properties of an object. TypeScript understands this JavaScript behavior and will allow you to do the same in your TypeScript code. Here we have a const variable called king that is storing the string Elvis. Now we know that const in JavaScript ensures that we cannot assign a different value to the king variable. An additional fact about JavaScript is that strings are immutable. That is, none of the methods on the string primitive type allow you to mutate the string value. TypeScript understands this fact and automatically infers the type of the king variable to be the literal Elvis. However, objects and arrays in JavaScript are not immutable. Here we have an object Dave with two members name and role of type string and a member skills of type array. Declaring the variable as a const ensures that we cannot assign a different value to the Dave variable. However, the object itself is still mutable, so we can assign different values to the different members, for example dave.name or dave.role, and even modify arrays by its methods, for example dave.skills.unshift. Once more, TypeScript understands this fact and automatically infers the name and roles to be of type string, so you can assign any string to them, and the skills member to be a string array. Now, of course, from what we know before, we can create a type specific to the Dave variable where we have these members, but they are all marked as read-only. However, there is another way you can achieve this effect without creating a type specific to this variable, and that is using a const assertion. Const assertions can be used on any value using asConst. Const assertions are essentially hints to the type inference that you wanted to infer the most immutable type possible. A const assertion does three things. It converts any primitives to their literal types, any members of an object to read-only members, and any arrays to read-only tuples. And now any mutations to the object will be highlighted as an error by TypeScript. In addition to providing immutability for objects, const assertions are also commonly required when you are working with objects that have literal members. Let's look at an example. Here we have a function called layout that expects an object with two members, a member align which is restricted to a limited set of literal types, and a member padding of type number. We create an example variable of such an object and then we invoke the layout function with this example. And even though the example variable follows the required structure, we get an error from TypeScript. If you hover over the error message, you can see that TypeScript is complaining that string does not conform to the literal types that are required by the align member. The reason for this error is that for the object example, TypeScript has inferred the align member to be of type string. This is consistent with what we saw in our previous Dave sample. We could fix it with an explicit type annotation for the example variable, or as we saw before, use a const assertion. With this assertion in place, the align member is inferred to be the literal type left and the error goes away. Notice that all the members of the object have become read-only and padding is also inferred to be the literal type 0. As mentioned before, the const assertion can be applied on any value and we can be more specific where we want to apply the const assertion. Since we only need the align member to be inferred as the literal type and we don't want to change the other members to their literal types or read-only properties, we can apply the assertion just to the left string. And now only the align member is inferred to be the literal left and all other members remain untouched. So when you are using a const assertion to fix an error, it is always recommended that you apply it at the most specific point possible. Now, unlike other assertions which essentially silence unsafe code, const assertions are just hints that increase type safety by limiting the mutability. So you can use them without worrying about your type checking becoming unsafe.